Hi everyone online. We'll just wait one more minute to let everyone come in and then I will kick off. Tēnā koutou, tēnā koutou, tēnā koutou katoa. And good afternoon, everyone. Welcome to Engineering New Zealand's Field to Insight MIDAS workshop. We're delighted to have you join us this wet, stormy and gale force wind Wellington afternoon, and hopefully those of you in the rest of the country are not suffering quite as much as we are. My name is Tania Williams. I'm the General Manager of Membership here at Engineering New Zealand. There goes our wind. And I'm delighted to be your host this afternoon. Today marks a real first for us, and we're really keen to get those of you online and in the rooms opinions on how this goes. This is the first time that we've partnered with a company like MIDAS, a structural engineering software company, to show you their tools and real-world applications. It's not about pushing products, but it is about making sure that our members know what's out there and can make informed decisions on what they do use. And at the conclusion, please do feed out the survey. There will be a prize, and give us your feedback on what worked and what didn't work in this. So we have a really full agenda, so I'm going to keep going now. It's going to cover structural geotechs, bridges, buildings, and dam engineering using the MIDAS software. This workshop will showcase MIDAS IT and how it empowers engineers to design smarter, safer, and more efficient infrastructure. Key takeaways will be advances in building bridge engineering workflow, including API-driven automation. Smart building design, I've taken some here on the guided tour on seismic analysis and performance-based design. Geotechnical solutions for slope stability assessment, and detailed analysis using finite element methods. So hold on to your hats. Whether you're a structural geotech professional or asset manager contractor, there's going to be something for everyone. And now for the public service announcements. Even if you fly with us often, no, wrong script, please note that this will count towards 4 hours. You hit it here, 4 hours of your CPD. Please log your CPD in the portal afterwards. And free stuff. All right, let me get this right. Some of you will have read this, but just to be clear, MIDAS has generously offered that all attendees will have a 6-month MIDAS CAD license, and doesn't stop there, will be provided with a complete suite of their software for the free for a year upon purchase of any MIDAS product. Clear? Yes. Excellent. But wait for it. They also are happy to provide project-specific, customized one-to-one training on demand. Very generous. Thank you, MIDAS. Right. Please feel free. Those online, we will have a question and answer session at the end. Please look at the chat function. Is it QA or chat? I'm looking at Q&A. There's a Q&A function. Please type questions in there as we go through, and we will ask them to the presenters at the end. Preempting your first question, yes, the slides will be available. And yes, we are recording this, and a recording will be sent out with the post-event comms. Right. For those of you who know me from my Thrive days, I had to fit a joke in, so just rate it out of 10. Why did King Midas suddenly drop his shovel? It had become a gold digger. Got some laughs. Okay. And now it's my pleasure to introduce our outstanding lineup of speakers this afternoon. You will notice, first off, that Edmund Kim was on the program, but he's replaced by Kanjaj Chandiramaji, the Regional Manager of Australia and New Zealand for MIDAS IT. Pankaj will introduce MIDAS's IT journey, global presence, and leading software solutions shaping the future of engineering. Then Wilhelm Stokes, project engineer from HOLMES. Wilhelm will show MIDAS Civil NX, how it integrates with Grasshopper and Excel, enabling smarter, faster, and automated bridge design for workflows. And Pranav Varshampuyan, structural lead MIDAS IT Australia, will take us through the evolution of structural design from traditional methods to next generation automated workflows, including seismic analysis of buildings using MIDAS Gen. Graham Roberts is the practice lead of dams for STANTEC Australia, and Graham will guide us through detailed dam analysis using FEA NX and highlighting the role of engineering judgment in complex design. And finally, Harsha Tadaviathi, the Geotech team leader for MIDAS IT Australia, will present slope stability assessment under static and seismic conditions with practical insights into NZGS guidelines. Hold on to your hats or crowns. MIDAS. Joke again. Come on. Room, you've got to get better at this. Okay. Once again, we'll encourage you to put in your questions. Those in the room, hold on to your questions, but we will ask you in the question and answer time. Last thing before I introduce our first speaker is there's a prize draw at the end where one lucky person will win some Apple iPods, things in your ears. So that will be drawn next week, but please, there will be at the end a 2-minute survey. Please fill in the survey. I'm sure in the room we've got an answer for that as well. And you'll be in to win those at that stage, but I'll repeat that at the end. So now, Panjaj, is the regional manager for Australia and New Zealand for MIDAS IT, with a strong background in civil engineering and has expertise in offering consultative guidance across Australia and New Zealand, the Middle East and African markets for MIDAS IT. He will introduce MIDAS IT's journey, global presence, leading software solutions, shaping the future of engineering. Please welcome Panjaj.
Test. Yeah. Kia ora, everyone. It's a pleasure to be here in Aotearoa, to be here in New Zealand. I'm Pankaj Chandiramani, working as Regional Manager at MIDAS IT Australia. I lead operations for Australia and New Zealand markets for MIDAS IT. With a background in civil engineering, I closely collaborate with design consultants, construction firms, government agencies to drive digital design innovations. I have experience of working with MIDAS for 8 years now. My focus is on helping teams choose and adopt advanced tools that allow teams to design safer, faster, and smarter infrastructure. I'm passionate about connecting software innovation with real-world applications and supporting the community in building better infrastructure together. Let me start by introducing MIDAS IT and a journey so far. MIDAS IT was founded way back in 1989 in South Korea, which was beginning of the software development at MIDAS. The first commercial product launch was made in 1996, and MIDAS IT was formally established in South Korea in 2000. And since then, we have continuously led innovations in structural and geotechnical engineering software solutions. The initial footstep in ANZ region was in year 2003, when we first secured our user here in ANZ. Just last year, in 2024, we formally established our Australian branch office in Sydney, from where we cater to the rest of the Oceania market from Sydney branch. Looking ahead, we also plan to establish a dedicated presence in New Zealand by 2027 to further deepen our local engagement. At every step so far, our mission has always been to make engineering simpler, more accurate, and deliver value products to our users. We are proud to be recognized as a global leader in civil engineering software industry with holding #1 market share, particularly in civil engineering industry domain. As we discussed, MIDAS IT is headquartered in South Korea, in Seoul. And yes, we do have presence here in Sydney, from where we cater to the Oceania market, while we'll have plans to strengthen ties in our Kiwi engineering partners. MIDAS IT operates from over 25 offices globally and has distribution centers in around 120 countries. Our softwares are used by more than 18,000 consulting firms with about 2 million licenses distributed worldwide. This clearly reflects the trust global engineering companies place in our software solutions. And to cater to our users in the best possible way, MIDAS IT operates with more than 1,500 professionals internally. Our business is mainly divided into two areas. Firstly, the software development, where we create state-of-art simulation and analysis tools for bridges, buildings, geotechnical, and mechanical industry. Our second business domain mainly lies into the consulting services, where we offer specialized consulting services for complex infra projects. With experience of consultancy services, we are able to understand day-to-day requirements of end users, which in return is reflected in our software products. And with this synergy of consultancy service experience and software development, MIDAS IT is able to offer a practical solution through its softwares. Talking about the key clients that we have here in ANZ region. In the region, we are trusted by several leading consultants, contractors, and government agencies. Our users, particularly in the government segment, are like TFNSW, Department of Transport and Planning, Victoria State, Main Roads, Western Australia, Public Transport Authority from Western Australia, Hydro Tasmania, Fiji Roads Authority. These are a few from many other government agencies who have adopted our software so far. MIDAS softwares are widely used by local and regional consulting firms as well, such as HOLMES, Becca, GHD, RoadLab, Novara Design, DamWatch, Gaia, Tasco Consulting, and a few others around in New Zealand. On top of that, top tier 1 consulting firms such as STANTEC, Oricon, Jacobs, AECOM, SMEC, WSP are a few other from the many power users that we have around here in ANZ region. We have seen growing adoption, especially in New Zealand market, and we are excited to continue that momentum, spreading out the MIDAS softwares. Now let's talk a bit about the family products that we offer from MIDAS. Talking about the bridge and structural analysis design tools, MIDAS Civil NX is an integrated platform for analysis and design of bridges and civil structures, which is built for modern infra needs. From simple culverts to girder bridges to long span cable stayed or extra dose type of bridges, MIDAS Civil NX combines advanced finite element modeling, design automation, code checking, all in one intuitive environment. It's designed not just for analysis, but truly to optimize each and every step of bridge design process. Here are a few of the examples and real-time project applications of MIDAS Civil NX from New Zealand. Projects like Parahike Bridge, which is the balanced cantilevered segmental box girder bridge, having 300 meters of main span. Next one is the Manawatu Gorge Eco Viaduct, which is steel composite multi-span bridge, both designed by Oricon and WSP in New Zealand. Similarly, the Prescara Point Pedestrian Bridge, which is 3-span continuous steel bridge with 100 meters overall span, 70 meters in plane radius, as well as Oram's Bridge from the Southern Corridor Improvement Project, which is a 5-span simply supported steel composite I-girder bridge around here in New Zealand. Moving forward, one of the iconic extra dose bridges from New Zealand, Weti River Bridge in Auckland, was having 100 meters of main span, was also designed by Oricon and RoadLab together using MIDAS software. Okahu Viaduct, which is a 7-span continuous steel composite I-girder bridge, are a few of the real-world project applications from New Zealand. These projects represent the type of collaboration we aim to build further in the New Zealand. blending global expertise with local engineering requirements. Beyond the ANZ region, MIDAS software has been used in some iconic projects worldwide, from medium to long span bridges. These projects highlight the reliability and scalability of our analysis software, whether it's a local culvert project or a multi-kilometer suspension bridge. MIDAS is capable of doing that. You would see a few of the examples along the way, one of which is Roth Duck Viaduct, which is a pre-stressed eye-girder composite bridge. Iconic projects from Thailand, from Poland, which is a flyover bridge having steel composite eye-girder bridge. This is a Russky Island bridge from Russia, which is one of the longest cable-stayed bridge, having 1.1 kilometers of main span and total span of 3 kilometers. Tuan Fog Bridge, which is a suspension bridge, wherein MIDAS Civil NX was leveraged. Moving on, for building structures, we provide tools that integrate structural analysis, seismic design, and code-based checking. MIDAS building solutions are trusted for their accuracy in linear analysis, non-linear analysis, high-rise modeling, and wind and earthquake performance simulation, which in a way becomes increasingly relevant in the New Zealand context. Talking about our software solution for building, MIDAS Gen, which is an integrated software for structural analysis and design of buildings. MIDAS Design Plus is a structural component design and detailing tool. Few of the iconic project applications, MIDAS Gen has a wide range of applications, but right from small 3-story to 5-story commercial or residential structures to multi-story apartment structures, even up until high-rise iconic structures like Burj Khalifa from Dubai, which is one of the tallest structure worldwide. It does have application in the general structures as well, like airport terminals, metro station structures, as well as the iconic museum or stadium structures from around the globe. Moving on, our geotechnical internal solutions includes software called MIDAS GTS-NX. MIDAS GTS-NX is an all-in-one software for 2D and 3D geotechnical analysis, integrating both finite element as well as limit equilibrium methods, all within a single platform. It's widely used for projects involving retaining wall, slope stability and landslide assessment, liquefaction studies, deep excavation, pile foundation, and ground structure, as well as underground tunnels. What makes it more powerful is the fully 3D finite element capability with applications into 2D analysis, as well as methods, different methods for geotechnical engineering, all available within a single platform, unlike other fragmented softwares out there. Few of the applications of MIDAS GTS-NX includes foundation pits, pile raft foundations for high-rise structures, excavation pits for high-rise buildings, optimization of pile raft foundation for or underground structure applications, assessment of urban construction on existing nearby structures, metro lines, underground structures, as well as the pile raft foundation optimization further. Not just that, it does have application into embankments, as well as concrete dam analysis, as well as the it has applications for excavation works for in urban construction. It does have application in the tunneling segment as well. So if you have a tunnel which needs to be analyzed in 2D or 3D, it can be well catered within the same software. That was a bit about the family products and the projects from across the globe. MIDAS IT has global reach out. So in order to provide utmost service and satisfaction to our client, we have been hosting lots of trainings, sessions, as well as seminars, both online and offline as it gets possible. Through this collaboration, we actively apply we actively understand the needs of the clients, needs of the industry, and incorporate to develop that in our software. Here's a glimpse of the few of the developments which are engineered for New Zealand in our software. So you would find databases as per New Zealand standards, moving load definitions as per New Zealand standards. Not just that, even the codal checks available in the software as per the local standards and guidelines out there. You would be hearing more about this in the upcoming presentations, so stay tuned, and I hope you enjoy the workshop further. Gamihi, thank you.
Thank you so much, Panchach. That was really interesting and huge. Thank you. Right, and we're going to hold you to having a presence here by 2027. We got that in writing. Okay, it is now my pleasure to introduce our next speaker, who will dive into the practical bridge engineering flow. So Willem Stokes, the project engineer from HOLMES, New Zealand. Willem will show you how MIDAS Civil NX integrates with Grasshopper and Excel to enable fast, smart, and automated bridge design.
Thank you, Tanya, for the introduction, and thank you to Engineering New Zealand for hosting this, and also thank you to MIDAS for the opportunity. So, yeah, my name is Willem Stolk. I'm a project engineer with HOLMES based in Auckland. I've about 10 years of experience as a bridge engineer, based in South Africa, and then last 5 years in New Zealand. So today I'm going to share a bit with you guys in terms of, how do we use MIDAS NX? How do we use the new technology to look at how we can do things better, how we can do things smarter, with API-driven workflows and MIDAS. So I'll just quickly have a look at, what are the general challenges we have with traditional design? How do we go about making that a bit better through automation workflows? Again, just one step back, don't forget about things that did work and still work, and then having a look at, the new technology through the likes of the API functionality, things like Grasshopper, things like results extraction in Excel, and then some lessons learned along the way. So I'm not telling anyone to suck eggs, but how do we design a bridge traditionally? It's pretty straightforward. We do a concept design. There's some constraints. It has to go there. What is the material? What is the span? We go and model it in MIDAS. We extract the results, and we design the bridge. Right? Easy. It's done. Yeah, right. It's never that easy. Things always change. We start a concept design. We know a few things, and as the design progresses, things are always going to change. It's unavoidable. What are these changes typically? Okay, well, we've designed the bridge. Let's move it 20 meters to the west. Let's add a skew. Let's make the span longer. Let's add some more piles, because we did some more geotech investigations, and now we found liquefaction. Make the piles bigger. Oh, we need to increase the shoulder width on the road. Whatever that might be, we've designed the bridge. Now we have to do it again, and possibly again. So it's inevitable. We don't know all the things we need to know in concept design. So how do we go about making sure that if those changes come, that are definitely going to come, how do we go about doing things smarter, doing things better to stay within our design program and our budget? We have to find some workflows and ways around that to manage that. Now the question is, what workflows? How does that incorporate into MIDAS? And I guess that's the point of today. I'll share a bit with how we dealt with those issues at HOLMES, and how we make our lives a bit easier to still deliver on time and on budget. So looking at softwares, and Pranav later will talk about this in a bit more detail, but there's a lot of softwares around that now adds the capability of linking to MIDAS. Things like Rhino, Grasshopper, AI, Python, you name it. There's so many tools out there that now the API functionality just broadens that horizon and capabilities. Now, the big question is there a single workflow to do everything? Or is it multiple smaller workflows to do certain tasks? Unfortunately, there's no silver bullet. I'll just take one step back. Like I said, before the API functionality, there were still ways of doing things better through what MIDAS calls MCT, which is a text-based input. And there are lots of tools that's been developed over the years that use this for better workflows. And yeah, with time, all of those automation workflows will inevitably turn into some API for automation through the new Civil NX. I'll just look at 2 examples of where that's used and how we've incorporated that and how we will incorporate that with the new API functionality as well. Again, we need to do things better. We need to do things smarter and faster. And we need to get rid of the repetitive nature of doing the same tasks 2, 3, 4 times as the design progress. This is a simple example of setting up a spreadsheet with inputs that can generate a model. And yeah, this works really good at the moment. That gives us a initial model. It works great, but once the model has been created, there's no further functionality, and you now need to do things manually. So with the new API functionality, this tool can be changed into something that becomes more automated, something that becomes live, and can be updated as the design progress. And like I said, inevitably things change. This also allows us to find workflows where we can get consistency across multiple teams, and we can do things in the same way, and we can ensure better quality through the process. A second way, just that I've definitely used a lot, I don't know who of you have had to deal with geotech information and PUI springs. Those things always change as the design progress, and it is very, very time-consuming process. So finding smarter ways, finding better ways to get those things updated as the design progress. And like I said, the API functionality will make that quicker and faster, and I think Pranav will have a look at that a little bit later as well. Now, to get into, like I said, the smarter things that we can do is, let's have a quick look at how we've used Grasshopper, how you use Rhino to create these workflows, to create these automations, to do things better, to do things smarter. I'll just show you guys some examples of where we have used it. It sounds simple, but we just look at a simple gantry structure across a motorway. We don't necessarily know where the gantry is going to go. We don't know the span lengths. We don't know the side constraints. So how do we create a workflow where we can automatically update geometry, which would inevitably automatically update the design, and without having to do rework, without having to resize members? So that's just a simple example of a Grasshopper script being used to generate a model where results is then, the model is automatically generated in MIDAS. Those results are extracted and the design is automatically updated as the site constraints change. Another very simple example, just a simple example of creating a box girder in MIDAS. As these things change, it is very easy to generate that if you've set up a workflow where it is a fully parametric model. Again, another just simple example, a truss bridge, same thing, an arch bridge, same thing. We can set up all these workflows where it becomes a parametric model, and we can do things smarter as things change during the design. Now, this is probably, I know Pranav will show you all of the fancy things that MIDAS can do. Probably one of my what I've used the most so far is using the results extraction tool out of MIDAS. Now, when we set up a model, the analysis is done in MIDAS. We still need to get those results out, and we need to do design. As the things change, as the span length increase and the bridge gets wider or the piles get deeper, those results need to be then re-extracted, and the design needs to be updated to account for those changes. So how do we do that a bit more efficiently? MIDAS Civil NX's API functionality makes that really nice, where it automatically connects with Excel, and any changes to the model will automatically update all your results. And through that, we can just do things better. We can do things smarter as a change. A very simple example is we have a pre-stressed bridge, concrete bridge, which in New Zealand is pretty standard. That just shows a typical workflow of results being exported to Excel. And as things change, the design of the structure is automatically updated. We've used this, and it is a significant time saving in rework, especially with a pretty standard way of using pre-stressed beams across New Zealand. The more we standardize that, the more we can do things more efficiently overall, instead of having to reinvent the wheel every time. So I guess from my side, a few lessons learned through the process of using these tools. And look, I'm still learning. MIDAS is developing on a daily basis, and they are bringing new and smarter tools with the innovation. And again, like I said earlier, there's no silver bullet in terms of doing things. Yes, workflows make it better, but you have to find ways. There's always going to be caveats. There's always going to be a missing thing here or missing thing there, but we have to be flexible to find better ways of doing it. A lesson from my side is it's a little bit better and it's a little bit easier to have smaller workflows which can do maybe individual things, instead of thinking of this as a project from start to finish. We can't automate a design from concept design all the way to detailed design. We need to break this into more workable packages, changing the soil parameters or changing the geometry of the bridge or whatever that might be. If that workflow becomes too big and too large, then it does not really it becomes less and less adaptable. Like I said, yes, there's no one size fits all. No site is the same. No structure is the same. The constraints at each site is different. So we must make sure that we design these workflows and we design our whatever we do to be adaptable, to be someone else to be able to change it. Probably the biggest lesson learned from our side is when you create workflows, it is easy to create a way for you yourself to do things smarter. It's really difficult to create ways for everyone to do it smarter, because everyone thinks differently about using these things. And yes, my point there on the screen, automation workflows are awesome. But we need, with every workflow, with every automation, we need to make sure that we put measures in place to make sure structural engineers still understand engineering. We can't just trust a black box. There's a famous saying, rubbish in equals rubbish out. So it doesn't matter how many workflows you do, you still need to make sure you understand what's going on as a structural engineer. So closing remarks from my side, there will always be repetitive tasks. The trick and the efficiency come from finding ways to do things better, finding ways to remove those repetitive tasks. Things will always change. That's unavoidable. But how do we as structural engineers find ways to do things better? Through MIDAS' API, through your own workflows, incorporate that, use the technology that is there, use the API functionality in MIDAS and find better ways to do things to save time. Technology is rapidly evolving. I don't have to tell any one of you that AI is developing at breakneck speed, and I'm not sure if anyone can keep up, to be honest, but we need to make sure that we evolve as well. We think about new things. How do we use this API functionality? How do we think outside the box? How do we do things differently to stay ahead of the curve, to do things better? And then my closing remark is, you can create as many workflows as you want, as many automation as you want. None of that, no AI, nothing can replace engineering judgment. And we must always make sure we understand what's happening in that big black box. Thank you.
Thank you, Bill. can you just hold on? We've got a couple of questions. I'll ask the room as well, but we'll just read you the questions online if that's okay.
Can your software be used for forward works programming for critical assets such as bridges? Is it capable for modeling to establish a 4-year forward works program?
I think that's probably a better question for Pranav a bit later on. Look, I think from an API functionality, I think the possibilities is probably endless, but I don't know, Pranav, maybe you can answer that better than me.
Sorry, you mentioned, can you repeat the question again?
Sure. Can your software be used for forward works programming for critical assets such as bridges? Is it capable for modeling to establish a 4-year forward works program?
4-year forward works program. Is that correct?
Mm-hmm.
Oh, I'm actually not sure what 4-year forward works program mean in the first place.
I think it's a bit more driven towards maintenance. It's a difficult question.
Yeah.
Maybe take that one offline.
Yeah.
Yeah.
We will get back to him.
Okay. We have one other question online, and it is, does MIDAS Gen for building and MIDAS Civil already have integrated New Zealand code, seismic, winds, steel, concrete, timber, etc.?
I think, again, you have to hold that question for Pranav. He's the expert.
We'll get the questions after my presentation. Maybe
Okay.
they must be answered during the presentation.
Are there any questions for Willem?
Yeah, so you guys selected Grasshopper. What other tools did you explore before finally landing on Grasshopper, and why did you use Grasshopper over the other tools?
I mean, yeah, good question. I wouldn't say we've decided on using Grasshopper. I think it's going to come a lot down to personal preference, the skills that you have personally to use these tools and create these workflows. There's also the functionality to do it through Python, right? Or through whatever tools might work for you. I think from my side, Grasshopper is easy to understand and easy to learn, but it's a bit more personal preference, I think.
So that's, do you mean that easier to use as in text-based versus visual programming?
I think maybe easier to use for me personally, like I said, personal preference. Someone else might prefer to rather do it through a kind of Python based platform.
Oh, gotcha. Thank you very much.
Cool.
Any other questions in the room? All right, you can escape. All right, thank you so much. Yeah, the automation of workflows and the potential to transform bridge and everything else design is massive. I have to wholeheartedly agree with you in that the most important thing to us is the engineers still know the basics. Whatever tool you are using, MIDAS or otherwise, you need to be able to understand whether the answers it's giving are realistic. And the only way you can do that is understand from first principles and make it up. As an aside, if anyone is interested in AI, and we will put some MIDAS stuff on there, we have on our website, Engineering and AI is one of our programs. We have a whole suite of tools to help people to embrace AI. We have a newsletter monthly that shows advances that engineers should be aware of. So if anyone is interested in finding out more about what's happening in the world of AI for engineers, please have a look at those resources. So now, what highly anticipated, now we'll explore the evolution of structural design and traditional methods of advancing automation. I'd like to welcome Pravna, and I'm sorry for not getting your surname, but I'm going to go Vaishampadre. Can you say it? Yeah, you'll correct me. I apologize profusely. So is the structural lead of MIDAS IT Australia and has extensive global experience across the UK, Europe, India, Southeast Asia, Papua New Guinea, New Zealand, and Australia, delivering innovative engineering solutions. Will take us through the evolution of structural design from traditional methods to next generation automated workflows, including seismic analysis for buildings using MIDAS Gen. Please welcome.
Thank you, Tanya. All right. Good afternoon, everyone. I hope it's okay. Yeah. And it's a pleasure to be here with you today to explore a subject that sits at the heart of modern engineering innovation, which is technological advancement and evaluation of tools over the years. So for decades, I believe structural engineers have managed to navigate the gap between concept and construction. But I believe today that's changing fast. We are in a new era where intelligent automation is not only eliminating repetitive workflows, but it is reducing human error and also accelerating project deliveries. So in this session, we'll explore how the latest software solutions are integrating geometry, logic, and design in a ways that are, I would say, not only smarter, but even transformative of how we build and design. So, and yeah, personally, since I'm most familiar with MIDAS tools, I'll be using that extensively in this presentation. Okay. So these will be the contents. And yeah, again, nowadays, I believe project margins are shrinking, costs are going up, and technology is evolving faster than ever. So to cope up or to cope up with the market, I believe project delivery should be efficient. It should be within limited amount of time. And also we should be considering or be complying with the standard codal clauses. So let's understand this in the presentation. So let's take a look at the very first part, which is time optimization, and also understand how technology is evolving with understanding the advantages and disadvantages of every step. Okay. So the very first one. All right. Just a sec. Okay. So first one, UI modeling. So this is a typical way of modeling from the time where software were first introduced. This is just a UI modeling procedure within MIDAS. But I believe this might be very useful back then, but evolving technology, even this procedure had to change due to a couple of reasons. Firstly is reliance on multiple sources for a preliminary data. I guess William has mentioned material sections which to choose or which to prefer for. Second is time intensive manual inputs if you need to modify anything, change anything, or for matter of fact, even result extraction. So for every revision, we need to extract results for every other scenarios, and it is a very time consuming process. And it is also with UI modeling, it is prone to user oversight. It is difficult to reproduce the same results. And I believe limited flexibility with the iterations. Mainly time is a very big constraint when we are going with the traditional UI modeling. So then what would be the way forward with this? So we can think of Excel. Since every engineer is familiar with Excel the most, we can use of Excel as a centralized platform and automate workflows through Excel, which will help us reduce all the time which we are manually spending on the software part. So I believe this gave your idea of how manual UI modeling can be conducted within MIDAS, definitions of material, defining the entire geometry, structures, and extracting the results. And if we intend to do the design within the software, we can conduct design as well. I believe this was an example of a steel composite bridge in curved span. Select elements for design. I'll just skim it through. Check the capacity of few sections and obtain the detailed design report from the software. Yeah, the design guide as well. Okay. So now let's see if we do switch to Excel. All right. Okay. And choose it as a centralized platform. So this Excel template is shown here is a similar example. It is a completely automated spreadsheets wherein the entire geometry section, model, load, construction stages, everything is automated. Even result extraction will be is automated in the similar workflow. And with Excel, as long as the Excel template is used for that intended purpose, maybe for just steel composite bridge without with zero radius or without no skew, it works like clockwork. So we can use it n number of times. It is very efficient, very seamless. But as soon as we try to make any changes to the existing workflow, most of our work is disrupted because we need to change all the automation, check every step of what the material is created, how the geometry is changing, how the geometry is aligning with the loads which are input. So I would say for fresh models, yes, this is a very good workflow and engineers have been using for a long time. But now when there are revisions, again, if we need to add a skew or if we need to change the radius, I'm not saying it is not possible. It is a bit difficult with Excel. Now then engineers had to look for another option. So what would that option be? So it will be graphic and parametric tools such as Blender or Grasshopper. Okay. So for this video, we see entire bridge was modeled and the results were extracted in Excel itself and also the images for report generation and documentation. Again, this works very well for a typical bridge, specific bridges. Okay. Now we have established that for fresh models, either you go with UI modeling or with Excel workflows, it will work very well. But what if we need to add parameters? As I said, change the skew, change the alignment. Then there the parametric tools such as Grasshopper comes in place. This is a simple example of how it can be parameterized. So here we are already created the model with Excel or with UI modeling. So now we will add a parameter to change the alignment. It is very good if you parameterize the entire structure from Grasshopper itself, but we can also use Grasshopper to add parameters to a few necessary elements. So over here, it's an example of changing the alignment. So we imported the nodes in Rhino, defined an initial curve and a final curve so that the offset reference to move all the loads and the boundary conditions are present, and then we can update the geometry. So I believe this is much more quicker and efficient with Excel. Again, I'm not saying this is a better version, but I believe engineer has to choose or which tools he has to use for a specific tasks. Okay, now limitation with such tools. These tools are easy, but this does require an urge to go beyond just the structural engineering domain. And also with commercial tools such as Grasshopper, there is a cost associated with it. So again, the accessibility is limited. Okay. Just on this, and another example of aligning or modifying the skew for the specific structure. So we have seen just changing the alignment, and just for the skew angle, we have used Grasshopper. All the manual modeling was done by the core software. So as I said, there is cost associated with it. Therefore, the accessibility for such tools are somewhat limited, I would say. What is the way forward with this? Then engineers tend to move to Python. We'll see why Python would be beneficial. Okay. So Python and why it is gaining traction. So first is versatility, and it is its integration with modern tools and APIs. And also Python, I believe in 90-95% of all the AI tools which are being developed, it is based on Python. So therefore Python is widely accepted. Obviously it is widely accepted not only in structural engineering, but even in other domains of engineering. So let's talk about standard libraries in Python, which I believe will be the major asset for anyone who are using the libraries. So I believe everyone must have heard about standard libraries of Python, such as NumPy, Pandas, Matplotlib. These are typical libraries which are very famous. Similar to those, based on the similar concept to reduce the workflow, MIDAS has created its own Python library. So it will reduce your entire script to easily readable syntax, I would say. This is just a list of all the components of library. If an engineer requires, he can also take a look at all the backend coding of the library. It is free for, or it is open source, I would say. And for the engineers who just want to get the job done, directly use the library and do any specific changes. Okay, so just on this part, we can see this, I believe hardly 7 or 8 lines of code is written, and entire bridge structure would be generated with this. So length is specified, width, skew, and number of diaphragms. And RCC T-girder is an example over here. So materials, sections, geometry, boundary conditions, loads, and even analysis is integrated with this single tool. So we'll be in that just single line. Engineer need not spend much time, just understand the code first and then generate the model quickly. And I also mentioned versatility. So how Python can be used? So it can be used to generate drawings. So instead of using any intermediate tool between analysis software and the drawing part, we can directly generate drawings from the analysis tool itself. So it can be done with the help of Python. So for the same structure, the RCC T-gutter structure, which we generated in the previous video, we can create a DXF format. Again, this library is Python own library. We have just used those library, integrated it with MIDAS API, and the drawings will be directly generated from analysis tool such as MIDAS Civil NX. So this, I believe, will help save a lot of time in the markup drawing stage, which every engineer draws and then sends it to the draftsman, get back, make the changes, and this goes to and fro. So instead, just a ready DXF file can be shared to the draftsman. All the plan view, element details, sectional details, everything can be extracted from an analysis tool. Yeah. So we can see rebar annotations, reinforcement details. Yeah, complete thing. And yes, so I believe we have had clients who are using the AI or API until this point with Python, but then how should we prepare ourselves for the future? Yes, AI is something which is very big, and as William rightly said, I don't think so anyone will be able to cope up with it. But MIDAS is trying its best to implement AI in this drawing process, in its software products. So this is just an example of what we are working on. So we are calling this as LDM, meaning large drawing model. So once this is ready, engineer can simply open the required drawings. So typical procedure is if we have a past similar project, we open those drawings, take a reference of those drawings, replicate it for a new project, modify, and then create drawings again for the existing project. So this tool will be able to identify all the sectional details, dimensions, material details, and it will be able to generate an entire analysis model within MIDAS 7x. So it will read all the components from the drawing format. So all the information, general arrangement drawing, dimensions, material properties will be extracted, and a complete model will be generated in Civil NX. Then you can do manual changes, add parameters, use Python, Grasshopper to modify as per the own project, and then automatically generate drawings again from the analysis tool. So engineer need not have multiple softwares. He can just use single model file for model generation, drawing generation, and all the things. Yeah. And this is another aspect of how AI can be utilized. This is just something which we are trying on with help of prompts. So let's see how this gives an idea. So we will be able to provide prompts. It is not developed yet. It is still development. So yeah. So a prompt to create a frame structure. We just specify what base, height, width should be provided. If you need to save, just write save the model, the folder location, and the model will be saved at the respective location. Just another example in this tool is to create a grillage. Again, this was just a conceptual stage, so just limited training. But we can see how prompting can be one of the use case, how AI can be implemented with the softwares. So create a grillage of so and so length, width, spacing, and a skew, and a grillage model would be generated. And just to give you a bit more of an insight of how everything will work. So I think it will be appeared in the video. And yeah, so basically a Gwen 3 1.7b model, yeah, this one was utilized as an AI to generate the scripts, and anything LLM was used to train the AI on the MIDAS library. So this is how on the backend it will work. So we just in the prompt, we're just switching the span lengths from 20 meters to 50 meters and click on generate. It will generate an entire Python code, and this Python code is backfed to the software with the help of API. So this is how the entire prompting function with AI and MIDAS 7x will work. All right. So Improving efficiency is always, I believe, what everyone strive for. But as I mentioned, it should not be at the cost of compromising any codal compliances, accuracy, and local industry practice. So now let's take a look at how MIDAS helps us align all of these things together in the second part of the presentation. Okay. Now in this slide, I have included all the NG specific features or which are favorable by our clients over here. So I think we are all aware that construction staging is one of the very powerful feature of the MIDAS. We can simulate every stage of construction and accurately capture the material effects or time effects, be it creep effects, shrinkage effects, compressive strength effects. So again, as per standard NZS bridge manual, these are available within the software tools. Next up are the NZ standard local sections. So these are mainly the precast sections which are widely used locally in New Zealand. Super T, I-girder, hollow core, or Super HI. Super HI, I believe it's a new and upcoming section which will be widely used in the New Zealand region. And also tendon automatic generation for all of these sections is already present in the software. Next up, so non-linear boundary conditions. So especially in New Zealand as opposed to Australia where the linear conditions are used, in New Zealand, the non-linear functions are used to represent soil structure interaction. And yes, it is a very time consuming task. We receive the properties of these nonlinear functions in Excel sheet. Then we define the graphs first, and then we define the springs at different levels of the structure. So now for such scenarios, and automation is already in place. Let us understand how this automation will work like. So left-hand side is a basic bridge structure, and on the right side, Excel sheet where the force deformation functions are present. It will be a two-step process. First, to import all the graphs of nonlinear functions into the software. So we can see all the graphs are imported. I believe there are 25 graphs. Yes. Step 1, and then step 2 is to assign the functions at respective depth through the soil and also generate the piles as well. So a reference node is provided such that the reference for the specific locations of the spring can be determined. Top nodes from which the piles will be created are selected. So we enter the same information in Excel. And then section ID and material ID. So which sections and which materials to be assigned to the piles which will be created. And once this is all set, we can simply click on create piles. And one by one, all the piles will be created. And also specific force deformation functions will be assigned at respective depths. So all the revisions you have can simply use this function, n number of revisions, multiple springs, even if they are obtained n number of times, we can keep using this functionality as is. Next up, so standard NZ vehicles. So all the vehicles such as HOHN, general access, 50 max, fatigue vehicle, deck evaluation, these are all the vehicles which are available in NZ bridge manual. These are all a standardized option within the software. To go into more specific, every vehicle has a particular tire area. So usually in plate kind of elements for bridge deck, if we consider a area load rather than a point load, we obtain a better force distribution. So that also can be considered within the software. So we can obtain a moving area load instead of a moving point load for plate elements within the tool. Okay. Also, the next one with moving loads is the dynamic factor. I believe this is very unique to NZ, that for every output of moving load, be it positive movement, negative movement, shear force reaction, there is a different factor associated with it. So even for an element which is going into positive and negative movement for different load case, for a single element, there is a different factor. So again, that also has been considered within the software, which has been automated, I would say. So all the outputs with all the respective factors will be considered and the result will be obtained. Next up is response spectrum. Yes, this is again a direct option. Select the soil, maybe probability factor, other parameters, generate the response spectrum curve and use it in the analysis. But the main challenge is combining the response spectrum and the soil nonlinear function. Response spectrum being a linear analysis, it cannot be utilized directly with the nonlinear property which we have defined in the soil. So for such scenarios, we have developed a tool, which is, we named it as iterative response spectrum. So let us understand how does this work. And this follows a similar procedure which we have discussed with the clients in New Zealand. They used to do this manually, but now a tool has been developed for such purpose. So whenever a nonlinear function is assigned for the bridge and we conduct a response spectrum analysis, all the nonlinearity is converted to linear spring, considering the initial stiffness. Once it is analyzed, a displacement is obtained at each and every spring location, and we assume a particular tolerance. If the displacement is outside our assumed tolerance, then a secant is drawn from 0 until that displacement in the nonlinear function. Now a reduced stiffness is obtained. And again, response spectrum analysis is conducted. And this has to be done repeatedly so many times that all the nonlinear springs in the model should be converged within the tolerance limits. So we understand that this must be very time-consuming process. So again, a tool has been created in this place for such scenarios. So we can see the same structure which we have been seeing in this presentation. There are nonlinear functions. This has been developed with Python. So when we execute the ITR, iterative response spectrum script, it is using a boundary change assignment feature because that stiffness has to be just used for the response spectrum and not for the static cases. Tolerance is assumed. Again, obviously a playback speed is applied to this. So, but we can see a live convergence graph as well, and the spring values which are updated at every iteration. So in each iteration, software is comparing all the spring location with the tolerance limit, updating if outside tolerance limit and putting it back into the software. So around, I would say 12 iterations were conducted, and then the software has finally converged. I believe manually it would at least take a week for such updation and iterations. And also a debug log in Excel format of what are the steps, what are the maximum tolerance at each step is observed. Okay. Another typical analysis which have been observed in Australia and New Zealand. In Australia, again, it is a linear analysis, but in New Zealand, it is non-linear springs. So it is called as soil sensitivity analysis, wherein we already have the soil nonlinear functions. Let's say they are of 100% stiffness. Then a different model or different case is created where the stiffness or the P, so force deformation, the F is reduced to 50% value divided by 2. And a third scenario where the F in the force deformation function is multiplied by 2. It is increased to 200%. And a sensitivity analysis between all three models is conducted, and the results are compared, and it is designed for more critical values. So again, this has been automated within the tool. Let us understand how this works. Again, same structure where multilinear springs are present. Let's look at the inputs first. So scaling percentages, we want to scale it to 50, 100, 200. ITR specifies it should go through iterative response spectrum analysis, AN just regular analysis. Name of the model and the location where the model is saved. And for result extraction, the load case, structure group, and the support groups whose results need to be extracted. So when we execute the ITR script, first step is to create the different cases where the spring stiffness are scaled to 50%, 100%, and 200%. So step 1, create models with different scaling percentages. So it will create, and the first one, the 50% scaling was set to ITR analysis. So the iterative analysis which you have seen in the previous present slides is being conducted over here. So it will also give you a detailed overview of what are the displacement tolerance and the terminal view of the Visual Studio. After the analysis is complete, as it's converged, then it will automatically extract the result and save it in an Excel sheet in the background. Then next up, it will open the second model. So all of this with a single click, it will be conducted. Second model, SSA_100. It will be analyzed, and also its results will be extracted in an Excel spreadsheet. You can see the UI of the software changing because it is actively extracting the results from the software into the spreadsheet. Yeah. And finally, the last model, which is SSA200. it will automatically open that model, analyze it. So there can be multiple models. These are just 3, but if you want to test the sensitivity for different scaling percentages, 75, 125, you can add multiple models, and all of these models will be analyzed, scaled, and results will be extracted with a single click. All right. Script summary of what are the extraction procedures. If there is an error, it will also give an error that this is the error, please change this. And finally, we'll look at the Excel sheet, where the script has been combining all the results. So all the 3 results, 50%, 100%, and 200% scaling, are compiled in one Excel sheet. These are the beam force results, then the displacement tables for all 3 models. So we can compare, and in a single view, we can have a glance of what are the results, different models. And also result images are also extracted in Excel spreadsheets. All right. Yep. So this was about soil sensitivity analysis. And next one, just very brief about this part, pushover analysis. There are also going to be a demonstration of pushover with building structures. So maybe we'll understand more about pushover in the next slides. Then just to show that this is also a functionality within the tool, which is dynamic nonlinear. If you want to maybe specify a base isolator, shock transmission units for our structures, yes, that can also be conducted within the tool. And the inelastic time history analysis, I believe most advanced seismic analysis, it is also possible within the tool, also with fiber hinging. So either we can use fiber hinging or moment curvature or rotation kind of hinge properties for the model. And yes, so to sum up my entire presentation, I believe traditional methods will always be there, but as engineers, we want our tools to build design faster, safer, economical, and also optimized. So yes, automation is something which was considered fancy in the past, but with all the resources which are available lately, it's on all of them being just a click away. We believe it is something easy and easily achievable. And yes, for all this, we at MIDAS are always there to help you at every other stage. So not just yet, I might continue with my next one. Yeah. So this is a short bit, maybe about 10 minutes, with simplifying seismic analysis for buildings with MIDAS Gen. So this is just to give an idea, because I believe MIDAS is very well known in the bridge industry space, but just wanted to highlight the building side of MIDAS, which is using MIDAS Gen, and pushover analysis or seismic, which is very required in most of the projects in New Zealand, just to demonstrate the capability of the pushover side in MIDAS Gen. So I believe this is the typical workflow whenever we need to conduct pushover or performance-based design, I would say. First step is to assume a particular section size, then assume all the material sections and so on. Then we either, if you use response spectrum analysis, then go through that ITR iterative analysis to obtain a demand compatible secant stiffness. Then we design the particular section, and then we go for the pusher analysis to check the particular performance of a structure. If the performance is satisfied, all good. Otherwise, we need to resize all the sections, redesign, and repeat the entire process again. So not the entire process in the demonstration part, just the last step of pusher analysis with the building structures. I've considered an example. So just it will be, I believe, a 5-7 minutes video. I'll explain through the video. For those who are familiar with civil, I believe this is the same interface of civil, but just all the functions are for building specific. The UI, tree menus, unit systems are all similar. So there should not be much time to get hands-on with the tool. Just to give basic information about the model, materials, sections, loads are defined. So there is also a shear wall considered, model with automatic meshing feature within the tool, and some basic loads, earthquake loads, wind loads, and response spectrum as per one of the scenarios of the NZ code. So it is already analyzed, and we'll first look at the mode shapes, because in pushover, it usually depends on what kind of pushover load we are going to apply. Either it be a nodal body force, inertia force, or just a specific fundamental mode, either X, Y, or Z direction. So I think with the modal shapes. We have already determined the fundamental mode for X and Y direction. Then we'll start defining the pushover controls one by one. First with the global control. If there are any permanent loads, there would always be some permanent loads. So the permanent loads should be added first in the initial control. So after the deformation of the permanent loads, then the pushover analysis should be conducted in the deformed state of the permanent loads. Then set up some necessary options in the global control. So step 1 done. Step 2 is to define the pushover cases. So we defined 2 pushover cases, push in X, I believe LCX and LCY. Set up the iterations P delta, either we go for P delta or large displacement, which is geometric nonlinearity. Load control or displacement control method. I guess those are already familiar with civil. Most of the steps are similar, but this is mainly for the engineers who are working in the building sector. And then for the control node, we specify a particular node at the top of the structure, specify the maximum displacement at which the pusher should be restricted, and different load cases or different options to apply push load. So over here we are considering mode shape. Mode shape 1 was very dominant in X direction, and for Y direction, we also set up similar push case. So I believe mode shape 2 for Y direction. So this completes the second step, is to define the loads for pushover. The next one would be to define the hinges. So in hinges, there are different types which engineer uses, be it moment rotation, moment curvature, either lumped or a distributed moment curvature, and also fiber type of hinge. Then we have different interaction types, PM, PMM, or none. So when defining the pushover hinge for beam elements, usually MY, and different types of hinges or skeleton curves, bilinear, trilinear, or as per FEMA and Eurocode 8 standard, are automated within the tool. And yes, if we have a specific skeleton curve, there is also an option to user define a specific skeleton curve within the options. Yeah, this is for beam elements. Then for column elements, usually the PMM interaction type, because actually it's very dominant. So we go for PMM interaction type for hinge for a column. So we'll just define that. So fx, my, mz, all of these degree of freedoms are considered for the hinging, capable of hinging. And finally, wall elements. So wall, which is modeled as a plate element, will define that with setup of a fiber model, just to explore the possibility that yes, fiber modeling is possible. And in this, we believe we can see how convenient and easy it is to specify a fiber model to the building element. So import the existing wall element, then we mesh the wall element with equal sizes, or we first define the materials. So different material models are directly available. For concrete material model, I believe Japanese code Mander model are available, or there are a couple of models over there. We'll just select the Japanese one for this one and specify the materials. For concrete, similar materials will be defined for steel. Again, couple of options for steel out there. Menon, Ghetto Pinto, and various others in Japanese code. And yeah, specifying the steel properties. Yeah, and then set up the entire fiber range model. This is just the concrete part. After defining the concrete fiber hinges, we will define the hinges for the reinforcement as well. Since this is already a designed wall element, all the reinforcement which is already designed will be imported into the same fiber hinge section. And yeah, so this completes our tedious process for the hinge definitions as per fiber model for wall. Again, the skeleton curve for the same is also there. And then after this, yes, we simply run the analysis. So pushover analysis. Oh, yes, we have to assign those hinges we have created. So for beam elements, then column elements, interior columns, exterior columns. and finally for the wall elements as well. Yes, after we assign the hinges, let's run the entire pusher analysis for both the scenarios, push X, push Y. And while it is performing the analysis, we also get to see a live pusher graph that is being generated over there. Once the entire pusher analysis is conducted, so for both the scenarios, X and Y. Yes, so this is the global pusher curve. And yes, if we need to obtain the pusher curve for any specific elements, that is also possible. So after pusher curve, we need to determine the performance point. So yes, for performance point, we can select the respective options. As per FEMA 440, there are 3 procedures of how pusher point can be calculated. And also as per ATC 40, which is closely related to our codal standards, we can use that procedures for the performance point. And yes, also observing the hinges or how the hinges are developing through the entire steps of pusher can also be observed. So the first step where all the hinges are linear, then we can see some turning into green, yellow, and then red. So different steps, IOLSCP, yeah, where hinge failing, and also yes, animated view, so we can see the progressive hinging of the entire structure within a single view. And I believe that's okay. The last part, it also obtained the pusher or force deformation or moment curvature curves for specific elements, as well as for the fiber hinges for the wall elements. Detailed fiber hinge results for every fiber hinge in the wall element. And yep, with that, I would like to end my presentation, and thank you so much for listening. I hope it was an interesting one. Thank you.
Thank you. Just told there we've got a couple of questions from online, and then I'll ask if there's any in the room.
Where can we get the plugin for the calculation of PY curves?
You can mail us ausupport@midascity.com and we'll send it to you.
Awesome. For beginners learning MIDAS, is Python knowledge required? I was also wondering whether the Python codes and Excel files demonstrated are automatically created by MIDAS or if users have to develop them manually.
So all the things which are developed by MIDAS, which are even showcased in the presentation, will be sent to all the users who are attending the session, or else you can also request us. And all the scripts within the software or with the external tools are open source. So you can take the script, learn the script on your own, and yeah, develop your workflows. Thank you.
So do you need Python knowledge?
Not to learn MIDAS, yeah, that's the right one. But yes, if you want to develop workflows, it is not mandatory, I would say. And we are also helping engineers. In fact, next month we have a training session we are using Grasshopper, VBA, and Python. So maybe the interested engineers can join the training sessions and experience themselves how Python can be utilized and how minimal inputs are required for your workflows. Thank you.
Any other questions in the room? No, thank you so much.
Thank you.
Wow, that was amazing compared to when decades ago when I went to school and did all that. Right, so we're running a little bit ahead of time. So thank you for those presentations. We're now going to take a 15-minute break. For those online, just leave it on. We will take away the sound and we will be back just after 3 o'clock. So about 3:05, but we'll leave it live, but you won't hear sound until 3:05. Those in the room, take this networking time. There's still food outside, and we'll be back at 3:05. Thank you. Welcome back, everyone. Hopefully everyone can hear me online. Right. So I hope you had a good break, good stretch. We're in for the home straight now. Some more really fascinating use cases here. So Graham Roberts of STANTEC Australia is up next, and Graham is going to guide us through the detailed dam analysis using FEA NX and highlight the role of engineering judgment in complex designs.
Thanks. Thanks very much. Yeah, so Graham Roberts originally from South Africa, but now in Australia, practice leader for Dam STANTEC Australia. Just want to see. There we go. Okay, so the presentation is advanced dam analysis and the enduring role of engineering judgment using FEA-NACS. The project I'm going to go through, I'm only going to cover the aspects of seismic analysis and then just something about sliding stability. I haven't covered aspects like thermal analysis or detailed stage construction. So it's not a complete review of the dam analysis. Yeah, so I'll give a short introduction, and that's just to discuss the geometry of the dam and how we'd expect it to behave, and then just a slide on the stress paths, and then the seismic analysis, sliding, and concluding remarks. So we do very detailed analyses. We saw in the previous presentation how many options and how advanced it is and automated. But at the end of the day, the models don't make the decisions, the engineers do. All we've been given now with these tools is more data, more information to make a more informed decision. Modern analysis tools offer the insight, as we've seen, but require professional and experienced interpretation. The topic of seismic analysis talks to understanding seismic performance under realistic demands, and the sliding stability will just cover Monte Carlo simulation to quantify uncertainty at the interface between the dam base and foundation. A similar approach can be done for abutment stability as well as lift joints. So, I don't have my glasses. I'm going to try and get that table. But essentially, this dam was actually completed in 1941. So it's aged infrastructure. And I think there's similar dams. This one's in Australia. There's similar dams throughout New Zealand. And I think as soon as you see that date, you automatically say, that was far before anything we have today. So there's a structure standing there. Did they design it for what we design today? And could they have designed it? In terms of seismic analysis, I think a common way to model hydrodynamic mass is using Vestergaard's added pressure or added mass. And the formulation of that just came out in, I think, 1933. So I don't even know if that was widely accepted at this date. So whether they designed it for seismic or not, given this is in Australia, is even a question. It has an upstream radius of 61 meters, crest length of 115, approximately 21 meters in height, and a base of 6.4. So we look at some ratios, and the length to height ratio is a 5.5. They are generally accepted numbers, especially in the engineer's corp. It gives some guidance to that. And then the base width to height also gives us an idea of how we can expect it to behave. The dams the old dams even dams today were pretty much designed on rule of thumb in terms of, or the set out in terms of your angle to abutment from the center of radius, that sort of thing. So you get fairly similar ratios within a range. I think this one, you can see the length to height ratio it basically will dictate a shallow curvature reduced arch efficiencies, which we'll go through in the stress plot. Thank you. You saw me squinting. So the geometry is it's a U valley shape, which again would lead to what you'd expect with stress flows. And the base to height ratio is 0.3. If you look at it by eye, you'd say it's a thin arch, which essentially it is. But if you can get thinner arches in a narrow V valley. And for this particular geometry, we'd expect the approximately upper 2/3 to have quite horizontal arching in terms of its principal compressive stresses, with the bottom third, 25% to third, being cantilever in terms of tensions, vertical tensions on the upstream and vertical compressions on the downstream. So again, before we've set out any analyses, you got this in your head what to expect. The design considerations, I've written foundation stiffness, uplift control, temperature, and contraction effects. Contraction effects is generally due to thermal drops. Luckily in this case, it's in a fairly uniform temporal climate, and generally in the olden days, they didn't build as quickly as we do. So there was quite a time duration between lifts, or a slow progression of building. So that also helps the thermal drop load case. I've got lots of time. So I want to go back here. When we go to site, there is one thing we look at. We observe the structure, and there are particular points that you look here. You'll see, for example, on the one, there's seepage, some lime deposits. Now, when you observe that, before you go back, you can also say those lime deposits would affect the interface or the lift joint strengths parameters in terms of friction, cohesion, and you can actually spot that across the entire dam face, and you can see spots are more concentrated than others. There's also seepage on the downstream apron, which shows you there's pore pressures, artesian pore pressures. So the uplift function is not going to be exactly like design. So just by observation, you can make these prejudgments of analysis. For example, there's deep bonding at the top. I could expect quite a lot of arching stresses to be there, and that would probably cause that debonding. So now we look at, this is just under hydrostatic load, so nothing else. And we go back to it now. And these are the principal compressive stresses. I know generally when people look at it, they look at the horizontal or tangential, otherwise referred to arch stresses. But I do primarily look at your principal compressive and principal tension stresses. Now, you can see, as I said previously, the upper 2/3 is pretty much a hoop stress there, very horizontal. And automatically that tells me when I look further that even if I get a vertical tension there, it's not necessarily the worst thing in the world because it's acting in hoop stress. So the only thing there that would really be significant is if there's a shear failure between those hoops. You don't get continuation of the arching. Then I haven't put this in there, but the the principal tension stresses on the upstream would be vertical. So just from looking at this, the model replicates what we could expect, and it's a positive outcome from the get-go. That's before we've gone any further. A key point to the construction here, and it's actually quite common in the olden or the older dams, arches, or thin to thin medium, is the keen, the pocketing. On others, there's actually discrete shear keys that they put in there. And that's why you'll see one of the biggest things on an arch is to try and ensure you don't undermine or deteriorate the downstream foundation of the center monolith. And then another key point is the shear keys. So those are the vertical joints that have a shear key. So again, you want locking in of that hoop stress. So those are generally things we'd want to move forward and check. Again, going for the seismic analysis, I generally have an equation in my mind. That's the equation of motion. We have your mass, your acceleration, your damping, velocity, stiffness, displacement, and that's on the left-hand side. So the way I see that is that's my model. That's my FEM model, my material parameters, my geometry, and then obviously damping. Damping is a very important one. I know there's rules of thumb, as in if you look at an operational basis earthquake, you use 5%. If you look at a safety evaluation earthquake, you use 7%. But it's wide. Well, it can be debated because there is Anil Chopra who has shown from testing on site that it can be as low as 2 to 3%. Again, that's prior to any significant damage. So that's a very important factor that can't really be pinned down straight away. And that's easy to define. And all of us define the FEA model on a day-to-day basis, whether it be a bridge or pushover, anything like that. Now, the key thing that we sometimes put a little bit less effort into is that acceleration, the seismic acceleration, the signal selection. And that's the one on the right. You can start with the response spectra, but for arches, for evaluation of existing or anything past feasibility, time history is the way to go. You shouldn't do response spectra on arch dams. So we're going to move forward on just a short discussion on that acceleration and how we look at it. So what we do is we take a target spectra, whether that be a conditional mean spectra, elastic spectra, whatever it is, and depends on why we chose it. That's our target spectra. So we will then go through a catalog of signals. You can select synthetic signals, not preferred, but you go through a selection of natural signals depending on the geology, the fault type, the VS30, the PGA, and you basically select signals that have a fairly similar profile to your target spectra. Then from there, it's never always on your target spectra. So following that, you need to actually look at frequency matching, which is what you see there. The blue line is the original, and this is only for one event. You normally select 3 to 4. The blue line is the original signal, and then the green line is the frequency match signal. Now I've written there massless and mass foundation. So massless foundation is been the way people have done it in the past. We're all familiar with it from a dam industry point of view. The benefits of that is that you don't get wave reflection and you don't get signal amplification or change in frequency of the signal. But you also don't get a fully accurate capture of the dynamic response of the system because you forgot out some of the mass part and some of the, so you generally don't get the exact same representation of a dynamic response. So I've written there for the mass foundation, we need to now be careful of using, although we've selected the signal with frequency matched, we need to be careful of what we're actually inputting into the model because the foundation, having a mass now, has its own resonant frequency, which you can see there. That's for like a column of swirl, just to give you an idea. So that was what, 4 and 3. So 3 is for the upper abutments, and the 4 would be generally below the dam. And note there's 2 different, so you'll get 2 different signals in the dam. And that's the stars shown there. So that's also a question in terms of judgment. Which one do we then target? Do we target the point at the base of the dam, or do we target the point at the abutments? So you can see the magenta line is basically if we take that matched signal and we run it, we can see we get quite a bit of amplification there. which essentially we could say, okay, we matched it, we put that in at the base, everything should be fine and dandy, but we're actually exposing it at the top or at the foundation to a much higher signal than it should be. So what we need to do is we need to relook at it. Now, the mathematically correct way and geotechnically correct way is to do deconvolution. So essentially, you develop a transfer function which says to, in layman's terms, it says, I have this input signal, or I want this signal at the top to be X. I have X, or depends, whatever layers of foundation you have. What must be my input signal to get that? That's essentially what it's saying. It's very difficult to do in 3D. So generally we do a 1D site response and deconvolution. But again, once you use that, you put it into the 3D model, you actually don't get it. So we need to now use judgment and say, do we, from a project point of view, do we go through that entire process, which can be quite cumbersome, specifically for, I'll deviate a little bit now, but quite importantly, do we do this for an isometric rock foundation? Theoretically, you have to, but from a project basis and judgment, you can essentially descale the signal. And you can see there that, I can't read the legends, but essentially you can see that once you descale it, you can bring it back to the spectra. There'll still be an amplification at the natural frequency of the foundation. But in the realm of the foundation reservoir and dam, that period is within the spectra. And for dynamic amplification, generally you'd want to take 0.7 of the forcing frequency and 1.4 times the forcing or the period of the structure. And if it's outside that band, it doesn't have as big an influence. So you could use that as a rule of thumb. Coming to deconvolution and selection, I've got lots of time. If you have, and this is particular for New Zealand with softer swirls and larger events, you can't take a spectra from a code. I think the Geotechnical Society might like that I'm saying this, but essentially you have to look at shear strains and plastic response of the foundation. So what one should do for complex geology, and that's why it's important knowing what geology is there and how it behaves apart from liquefaction, is you need to run a 2D analysis, because if you put, say, a G signal or 0.7 PGA seismic event in there, that 0.7 might not even reach the top because your shear strains might be so great, your swirl damping is large and it doesn't carry the signal up. But what it does actually do is it goes through period lengthening, or it changes the frequency content of the signal. And that's critical to know, and you can't capture that in a response spectrum from the code. Okay, that's my deviation. Now, what we do is we then, before I run the dam analyses, I run the analyses or time history on the foundation by itself without the dam, because the principle is you want to expose the dam or structure, whether it be a building, whatever it is, to a signal or that would be on foundation without any structure there. That's what it's doing, because the seismic events are generally measured at stations, which should not be too influenced by anything else. Okay, now for this particular dam, and you predefine how you want to model it, but for this dam, what we did is we split it into different monoliths, different lift lines. That's why there's a nice color plot there. Then we create the foundation dam interface, because that's one of the things I want to assess. We have vertical lift joints, because we want to see that engagement or disengagement. And then the bottom bit is it all put together. So it looks like quite a complex model, which it is, but what I found here's advertising for you guys. What I found good with MIDAS is it's got a very powerful automesher compared to other softwares I've used. The key is making sure your geometry is done, taken time, done correctly. And that I'll stress that with any FEA. Geometry right in the beginning is very key to saving time throughout the entire process. So if you do that right, you're pretty good to go. Now, in terms of not the interfaces, we have the dam, we have the foundation, and we have the reservoir that we put in there, the sloshing elements. What I haven't shown there is the free field elements that do also come on. Critical for arch dams, or even for gravity dams that are in quite a narrow valley, is doing a staged analysis for gravity loads. I have witnessed on projects where they don't quite do this. Funny enough, it was actually a gravity dam and in a fairly narrow valley. So if you put the dam all once or even two larger intervals, you actually get an arching stress under gravity load, which is incorrect, and then the rest of your analysis is incorrect. But it is definitely key for arch dams. And you can see there we go to stage 1 to 8 is once the dam's built up, and then we have hydrostatic loading or your design loading, and following that is the seismic loading. Advertising, the stage construction analysis is actually quite easy to set up, which is nice. You're left with a lot of time to do engineering rather than analysis. You do V&V, you do your checks, but it does give you that time in projects to do the engineering. Okay, so here's some pretty pictures. On the top left, it's actually an extract from FERC. Do note this isn't exactly the same kind of arches. This would be a V valley or narrow valley, possibly. And some of the things you want to check is, as you've seen there, the vertical interfaces, because if you lose that, you lose arching, which is essentially the stability of the dam, and your horizontal cracking, which would be your vertical tension stresses. So to review this, again, knowing this is what we want to do, we've already modeled the dam with interface elements. There is a shear key in there. So the interface elements, what's nice is you just leave the shear stress or shear strength elastic and check it afterwards, but you leave it elastic. The normal stresses, you can do elastic perfectly plastic. Generally, I put the tensile strength at a nominal 100 PA or 1 kPa. It's not a massive deal. It converges quite nicely. And on the top right is going to be, that's a principal tensions. So I'll just talk you through that. The bottom left is the relative opening in the normal. So we can, throughout the time history, tell what's happening. You can also do it in post-processing, but this is nice and visual for a presentation. The bottom right is, I've put that in there because it's a nice little check. So that's an extraction of the hydrodynamic pressures, or the pressures on the interface between the dam and the reservoir. Just the time history of the pressures, and you want to check if the model is right, and you want quick little checks. We have in-house tested with my colleague, might be watching, Ryan, that it does actually model the dam and the hydrodynamic pressures accurately, and we benchmarked against, I think it was a 2019 benchmark workshop problem for Committee A of ICOLD. So we did look at it, again, check in your work, and that gave good results compared to the widespread that you actually get. It was quite accurate. But for project specific, we basically, what I did is I took the Vestergaard's equation, calculated what your peak stress would be, equivalent. So you extract your acceleration at the heel of the dam. Then you put in Vestergaard's equation and you say, okay, where does our time history match with this? And you can see it's not exact, but it gives you a pretty good approximation. I don't expect it to be exact because Vestergaard's formulation was based on a rigid dam. Arch dams are extremely flexible, so you can't get the same, but it does give you some form of confidence in what you're getting. Here's my little videos. So this is going to be the relative opening, and the shear keys that we saw previously was approximately 150 moles. So now we can basically look at it and say, are we getting 175? What are we getting? And this is with the 0 tensile strength interface. So you can see we do get some opening at the top portions, but I think that's probably like, what's it, 2 moles or something, quite low and well within the capacity of the shear keys. Also oscillatory in nature. It's not instant, it's not constant. So by the time any debonding could happen under 0 tensile strength assumptions, it's re-engaged. So that's one check we've done now. And then another one that I'll talk, so this is the principal tension stresses. And you'll see they actually do get quite high. But one check that I am going to do probably in this next week is the lift joints. I'll assign a 0 tensile strength. And basically what you're going to see, or what I'm hoping to see, is the rocking effect and how it rocks. Because you do get on the downstream toward the upper portions, you get quite high vertical principal tensions. So you'd expect some lift joint opening to occur. And at the base, on the heel, you also get high vertical tensions. And that'll be debonding. But that, at the interface of the heel, when you get uplift and it peels away and you get increased uplift load and it peels away, essentially what that does is it throws more arch stress into the abutments and less shear demand on the center monolith. Less so with the wide U valley, but it does nonetheless. So that's just a couple of nice videos. Yeah, so look, there's a lot of other checks we do, but this is just for this presentation. So don't take us as I did these checks, the dam's fine. There's a lot of other checks that go into it. Okay, now one thing I want to cover here is, and then I think we need to give it consideration. It's sliding stability, and like I said, it doesn't have to be just the foundation dam interface. It can be the abutments where you get thrusts, lift joints, wherever you want to check it. Basically, in dams, what we do is we take a look at your peak pressure or peak strengths, shear strengths, and your residual shear strengths. And we check it and we get different, this is for gravity specifically, we get different factors of safety and there's different requirements in the guides. For the arch dam, you can see therefore, this is out of USACE. You get for your usual static, it's 2, for unusual, it's 1.3. So essentially you choose a friction phi and you then go and check the case. Fairly simple. Now, you've made an assumption on that, but there are so many different variables, is your jointing, your orientation, your joint orientation in 3 dimensions, how well it was constructed. You can see, for example, there, the disparities that you have. If under low normal stresses, it would have to ride those ridges to fail in shear. Under high normal stresses, you'd have to shear through that entire rock portion. Again, that's only because those joints are orientated as they are. You need to know your joint orientation. But this again points to the importance of engineering judgment, because we have a model that's a continuum, linear. We can do nonlinear, but I'll get to that point why nonlinear is important, but also can't be fully the end goal. So what's important, and I'm sure a lot of us have looked at this, is we got more Coulomb envelope. Now for rock or concrete, what have you, or in the interface, the actual curve of the Moore Coulomb is nonlinear. It's not a peak and a residual. Well, it's not linear. We want to understand at what pressures the structure is being exposed to. You can see there, depending on where it lies, your friction angle actually changes, your cohesion changes. And the interface between the dam, the concrete, and the rock is often stronger than, or very often stronger than the actual localized joint you might have just below it. I've actually seen that through coring. We've cored through this dam actually, from the downstream right to about the middle of the interface, and we've got some decent cores. So what's important to quantify when we looking at this, particularly for concrete on rock, that's what I'm talking about here, nothing else, is we want to capture our cohesion. We want to understand what our phi is. These are the variables. That will give us the first line. Then, as I said, because the interface between the rock and the concrete is often extremely competent, there is a direct tensile strength associated, and that's that blue portion there, which then we can define the other portion of our material parameter. So what happens now is we've extracted the interface elements, all the details in terms of the coordinates. And again, it comes to setting up your model. You don't want your model in an arbitrary position, because then it makes the rest of your post-processing difficult. So you set it up in the beginning. So understanding the structural response of the arch in terms of we got high compressive stresses at the toe, we've got low, or we've got tensions at the heel, and that could actually, due to the arching, and it depends on the shape of the valley, we can assign different zones. The zones can be numerous. If we do have a geological feature running one abutment of the dam or whatever have you, you can replace that with a different zone, a different material parameter. Again, this is all post-processing, but the post-processing is easy due to the ease of extraction and the compatibility with Excel. It would not really be as user-friendly if it wasn't. And for MIDAS FEAX, I'm looking forward to the API so I can do something that Willem's been doing. So what we do is we assign for the friction, for the cohesion, for the tension, we assign the mode, the min-max. This is in particular is for a triangular distribution. The key here to this whole procedure is defining your zones and defining your material distributions. That is quite an important factor here. And now these come into a lot into engineering judgment, because a lot of the times with existing dams, there's not a lot of instrumentation, not a lot of geological or geotechnical testing goes into it. I was actually very impressed with this client, his willingness to actually undergo or undertake drilling and testing. So I'm looking forward to that coming back, and I can define these a lot more accurately. So I think we all know Monte Carlo simulation. Essentially what it is you've got your distribution, a cumulative density function. and you use that to just randomly sample points, and those will be done for the zone. So we have our results extracted from MIDAS. We've chosen our distributions. We've got our material parameter, or our material strengths that I just went through now, and you can see the parameters there. And we basically calculate the shear, the sliding factor of safety for each as we go in iterations. I think we've got pretty good convergence at about 5,000 samples, which wasn't too bad. These are just the distributions. So I think what would be an important part of following this process is, once we get to the stage, we sit as a group of whoever the designers are or the checkers, and we sit and we say, these are the distributions we decided on. This is the reasons why, whether they be from geotechnical reporting, testing, or sensitivities, very experienced engineering. I mean, guys that are in their 60s, that kind of judgment. With all due respect, not like a 20-something-year-old, because you do need a lot of experience with this. And at the end of the day, following all those calculations, you can get, it's basically 1 minus the cumulative distribution function. So if you read off the y-axis onto the x, it's saying there's an 80%, let's take, for example, which is a nice one, I can't quite see. But if you take 0.8 across and down, that's saying there's an 80% probability of exceeding that factor of safety. What's beautiful about this as well is you get to understand the variability that's per monolith. And again, if understanding that the center monoliths, if they do weaken, they actually distribute that load to the adjacent monoliths, because we check the shear keys and they transfer quite nicely. And you'll bring the more robust monoliths, their factor of safety will slightly fall, and the central monoliths would increase slightly. Now we compare that graph to what would have been done in the past. Is we take the best estimate, or maybe our peak, let's call it the peak, and we take our residual, and we'd find 1 factor of safety. But are we able to speak to ourselves and say, okay, well, where do we stand? How's our feeling in terms of how has it changed? What can we expect? We can, but I also find this a lot more helpful. And in particular, one reason it's helpful is what's coming to play a lot more, and this comes to business decisions, is risk assessments. So they are very advanced. You got risk specialists that do this huge risk assessment, event trees, whether it be seismic, floods probably for Australia. And they've got these probabilities, and then eventually you do a seismic analysis. And what I've seen in the past is you do your analysis under an event. Let's say let's call it sliding for an event. And then there's a table of may happened, would happened, will happen, and then it's got a qualitative probability associated to that. So then what you do is you look at it and you say, you know what, I have an idea that it would fall into this category, and that goes into the event tree. And that actually gets used to make business decisions by owners, which is critical, because then we turn into money, infrastructure, where you assign your resources as a business. So this is one place where it would be powerful, because you could say my factor of safety required by the code is 2. What probability would there be that this could fail? And that could be used directly if the sliding stability is the driving failure mode I'm talking about. You could directly read that off, and that would go into the risk assessment. And it's a lot more educated, guess, I'd say, or scientific. No, the guess was a bad word. It's a lot more scientific approximation. So I do believe that this should be embraced a lot more. I know some people do use it, but I would want to bring attention to it, and it's it's not only used for sliding stability, it can be used for a lot of aspects, anything essentially that you've run a linear analysis on. So my concluding remarks, I think you can see now, if you set it up correctly, you know exactly what you want in the end. FEA-NX enables a deep insight into dam behavior, which allows one to make informed decisions and interpretations of your structure. It's fit for purpose modeling approach. You can go extremely complicated, which sometimes I do, but I try and not do it unless it's required. For example, I will do it if I really want to understand how I've looked at the probabilities and I've said, okay, this is the friction and phi I want to analyze it under. And you do a full nonlinear and you actually go to a failure mode. And you want to see how it responds fully. That's one way to do it. And it gives a very balanced perspective between detail, practicality, and computational effort. Because computational effort is two things. It's the cost of the project, and the more computations, the more time you spend doing the analysis due to commercial limitations, the less time you have to actually do engineering. And then we can distinguish, or know in the judgment, you distinguish between physical response vis numerical artifact, something that's produced, for example, a stress concentration, which I've also come across where we get a stress concentration and there's a real panic about it, but you can understand that is a concentration. And analysis informs, engineering judgment decides. So if we go straight away from linear analysis to nonlinear, or some people start with nonlinear, you got one data point. So your analysis informed one data point. We are leaning more towards quantifying reliability and I wouldn't say not deterministic safety. I would rather actually say which complements deterministic safety. I'd say it's a complementary and interchangeable relationship. Advanced analysis is a tool, and engineering judgment is the craft. And lastly, thanks to MIDAS for appreciate it, and Engineering New Zealand. Thank you very much.
Thank you. Stay there. We've got 4 questions online that we'll pose to you now.
Given that the earthquake motions database are relatively limited in New Zealand, what are the implications of taking overseas time history records in terms of frequency components for different rock properties? So,
for example, if you just take the west and east coast of America, they're completely different geologies. The west coast, I've interchanged, but the west coast is much more seismically active. I mean, you've got the San Andreas Fault, I think it's one of the biggest ones there. So for New Zealand, which is also seismically active, you just choose which database you want to sort of use. But more importantly, it's the fault typing that you want to look at. And that's what you want to then match it to. And also the VS30. That's one aspect you want to do, which is a criteria, search criteria, and your earthquake magnitude is quite a good one. But when selecting, I'd also look at the area's intensity of the signal. Generally, a slip strike gives quite a high one. But once you've got your target spectra, you can frequency match that, or you alter the signal. You just try and keep that to a minimum. That's the goal. You keep that to the minimum so you don't change the signal too much. Did that answer it?
Sounds good to me. A follow-up question. Is it difficult to find time history records with similar site to source distances and similar ground properties?
Not really. I know Europe, I think it's EMS has one. They've got quite a good database. That's actually another criteria that you can use is the epicentral depth. And is it Pierre in the States? I think it's Pierre it's University of Berkeley, California. I think they've got a research center that has a database that for minimal fee you can actually subscribe to. I think EMS is actually free. So yeah, you can get them. It's just, sorry to carry on, but when you do it, there are a lot of them. So you got to do it wisely, and generally there are systems out there to do that for you.
Thank you. How do you verify your ground amplifications are correct in a New Zealand context?
Well, I don't think it's only a New Zealand context, I think it's a world context. I think as you said, or as I showed there, I'd look at I model it without the foundation, and I first establish what signal will be my structure will be exposed to. I think I also touched on, in terms of New Zealand context, is if you do have lower strength material, that I would recommend doing a separate analysis. Specifically, at the moment, I'll just say it in like Plexus or something else like that. Flak's a good one. That's a finite difference, I think, though. I'd actually have a specialist geotechnical team look at that to develop the signals and go from there.
Thank you. That's all.
Thank you very much. Let's have another round of applause for Graham. And I didn't pay him to do it, but the engineering judgment is wholeheartedly what I believe. And in using these tools, it was very clear through Graham's presentation that you need engineering judgment, not using the tools as a black box, which is, of course, what we're saying. Now, those of you who have been waiting for the geotech section, it's up next. All right, so next we're moving on to geotech solutions with Harsha Tadavathi. Close. All right. Geotech team leader at MIDAS IT Australia. He specializes in advanced numerical modeling and brings practical insights into slope stability assessment using LEM and FEM methods. He will present on slope stability assessment under static and seismic conditions with practical insights on the NZGS guidelines. Please welcome Hashi.
Hello, everyone. Good afternoon. Thanks for the kind introduction, Tanya. So, yeah, I'm Harsha Tadavathi. I'm a geotechnical team leader and technical manager at MIDAS IT Australia. So, glad to be here representing MIDAS and collaborating with Engineers New Zealand and interacting with engineers in New Zealand. So, it's a different experience. So my topic for today's presentation will be the last one, but it's a basic one as well. So we are going to talk about, I'm going to talk about the static and seismic slope stability assessment via limit equilibrium and numerical approaches. So slope stability is like a pretty common project, like it is part and parcel of almost every project that you guys deal with. It's like around 50 to 60% of the geotechnical engineering jobs as well. So it's a basic one, but very important one. And in terms of New Zealand context, it becomes much more important because of the unique geology that is present in the New Zealand. So these are the contents of today's presentation. We will talk a little bit about New Zealand geotechnical reality. And I will also talk about a comparative study between LEM and FEM. And we will talk about a little bit about earthquake and how GTSNX, which is a MIDAS product that gives and offers solutions for various problems that we face in slope stability especially. Of course, GTSNX can be helpful for other projects as well, foundations and even the tunneling, and it can be applicable for rock mechanics as well. So yeah, that's the idea. Let's move forward with the first one. The engineer's geotechnical reality. New Zealand geotechnical reality. So like the northern part of the New Zealand, where we find a lot of volcanic ash related soils, and because of the highly seismic zone of New Zealand, slope stability is essential to be assessed for seismic assessment as well. So these are the major things. I have been traveling to New Zealand for over past 1 year, and after interacting with engineers and after interacting with the engineers at New Zealand Geotechnical Conference last week. So this is a very broad idea that I came up with. So highly seismic focused, and a lot of weather-driven failures as well. And because it's a highly seismic focused, so liquefaction, lateral spreading are the very important things. And in terms of weather-driven failures, rainfall is the very important part. And of course, the other climate failures, climate-related things like the temperature variations and other things is very important as well. But we will stick to rainfall in this presentation. And yeah, other focuses, other failures such as the rapid drawdown and climate changes effects are important as well. The two pictures that you're seeing right now are the rainfall driven failure. That's the failure in one of the motorways in New Zealand. And of course, the famous Kaikoura earthquake in 2016. So it's an earthquake-driven failure. There was a fault over there. And we will also see, I was able to create a small model that could represent the Kaikoura earthquake as well. So we will discuss about it in detail in the coming slides. But firstly, when you want to assess the slope stability, so we have various methodologies. The first one is limit equilibrium method. And in FEM, you have two different techniques. Which is the strength reduction method, or shear strength reduction, or C5 reduction. The technique is the same, but every engineer can describe it in various different ways, like C5 reduction technique, or strength reduction method, or shear strength reduction, one on the same. And in the next one of FEM for slope stability, there is one more technique called strength analysis method. So we have all of them in GTSNX. That's the important part, because most engineers deal with LEM, but for important projects, they deal with FEM. So now the guidelines have been enhanced, wherein MBIE as well as NJGS have included the FEM for slope stability assessment in their guidelines. So let's talk about LEM. So it's the oldest and the best known method. So hands down, it's the widest used method for the slope stability assessment all around the world. And the most important thing is, like the name itself suggests, it is limiting the equilibrium conditions. So like most of the things we simplify the failure surface like a circular failure surface, or we deal with a polygonal failure surface. And we convert this entire failure surface into number of slides, wherein we end up having 5 unknowns. But since we are having 3 equilibrium conditions, there is a need to limit the equilibrium. And hence we have various methods: Bishop method, Felinius, Yambu, Morgenstern Price, Sama, and so on. So this is very in general about limit equilibrium approach. And hence it has own pros and cons. It's very simple to use. And yeah, it has its fallbacks. And when it comes to FEM, so all the things that that we are dealing with LEM, wherein introduction of a slip failure surface or cutting the failure surface into slices is no longer valid. Here, they deal with the strength reduction method or the strength analysis method. So here, as you see in the picture, the right bottom, so that's the Moore-Coulomb failure envelope. For the initial state of the soil, the thick line where you can see the initial Moore-Coulomb failure surface. So for the in situ stable condition, that's how the failure envelope would look like. But as it becomes, as it comes near the failure, it touches the Moore circle where the failure begins. And that's what this strength reduction method or FEM technique does. So it keeps on reducing the strength, C and phi. It keeps on reducing the strength and until it finds a failure surface. That's how simple it is. And that failure surface, as a result, could be a circular failure surface or a planar surface or planar failure surface or a wedge failure surface, depending on the topography, depending on the input material properties, and so on. So that's the idea. So it has ability to consider all the equilibrium condition because it's FEM in nature. So since FEM can consider all the equilibrium conditions, compatibility equations, and boundary conditions, and all the constitutive equations, that's the important part here. Most of the LEM approaches or LEM methods are limited to elastic material. But if you want to consider the plastic nature, so the additional strength that you may find because of the hardening behavior or the nonlinearity, so all the additional strength that you may find can only be dealt with the constitutive equations such as hardening soil model or any other nonlinear models. So that thing can only be considered in FEM. So it is a precise method, and it has its own limitations until the previous generation, because we can say it's a highly computationally expensive thing. It can only be used for the important projects, but all those myths can be overcome. So that's what I wanted to talk about as well. So the myths are FEM is too complex. Use it when we have a complex job, and it takes too long for small jobs. So, but it is not the real case. So modern tools like GTSNX, it is user-friendly and intuitive, which makes FEM a go-to tool. No need for like always considering FEM for complex jobs. You can use it for small jobs to complex jobs as well. And since you're going to consider a lot of boundary conditions that may exist in the site, and the compatibility equations, as well as the constitutive boundary conditions, constitutive equations, it helps to reduce field trails that you may end up having after initial trail that you can have from the LEM methods. So it helps to reduce field trace and errors. And computation has been significantly increased. So with the advent of the GPU, as well as multi-core and as well as multi-CPU, like the computation has been significantly advanced over, I would say, last 1 decade. So FEM can be a go-to tool. And according to MBI, the Ministry of Business and in Infrastructure for Engineering, so and GS, so they have included FEM in their slope stability guidance as well in the October 2024 draft. So it is set to be released, I guess. Yeah. So these are some of the myths, and the facts is, yeah, you can go with FEM very frequently and for small to complex jobs as well. So I wanted to highlight some limitations that we have with FEM and what we can deal with that FEM as well. So comparative study has been made. So I created a very simple slope. We have dense soil, and the bench is like around 45 degrees, and cohesion of 30 kilonewton per meter square, friction angle of 36 degrees. The elastic modulus was wrong over there. The elastic modulus that I considered was 50,000 kPa. So this is the simple slope for the comparative study I created between LEM and FEM. So what we found is, in the case of LEM, we found the factor of safety to be 1.78. And the same thing has been found in FEM as well, 1.77. The strength reduction method has been applied. So the idea is, for a very simple slope and a uniform soil throughout, you would end up having the same failure surface and the same factor of safety, so which is not a concern at all, right? Both approaches are giving the same answer. And when you go over the earthquake, even during earthquake assessment, wherein in this condition I had considered the pseudostatic assessment, the horizontal seismic coefficient as well as vertical seismic coefficient has been provided. For this, I had considered the PGA of Kaikoura earthquake, so it's 0.22 G, and the horizontal coefficient has been considered like 0.5 times of PGA, which comes like 0.5 times of 0.22. And the horizontal coefficient was that, and vertical coefficient was considered like 2/3 of the horizontal coefficient. So that is what considered in this assessment. And we end up having almost the same result for limit equilibrium approach as well as finite element approach. because the soil has been uniform and all the other things. But yeah, it is the same thing that you would find in the uniform soil and very simple slope. But what if, for very simple slope, the FEM and LEM are providing very same results, not similar, it is the same results exactly. But what if we have complex slopes with multiple soil strata? So sometimes there might be a very thin layer, which is liquefiable in nature, and that is providing an challenge for the engineer, like maybe who might be dealing with pile foundation over there, or who might be dealing with slope stability. So thin layer could be of a very important concern for many engineers. So what if we have a very complex slopes with multiple soil strata? Is LEM going to be helpful there? So we will check it out. Also, if you're dealing with a soil and fractured rock, so if you're dealing with a fractured rock, it is explicitly needed to model it, or else at least needed to consider the rock mass properties. So is LEM going to be helpful for that? So we will find it out. And what if rainfall, a transient state, is to be considered? So the regular LEM approach, it considers the steady state condition. Of course, we run the seepage assessment in the transient, but at the end of the day, we take the final steady state condition to the LEM analysis and run the assessment for the slope stability. It is a kind of steady state condition, but you have a transient condition need to be considered at regular intervals. You would like to find the factor of safety because the stress state changes because of the rainfall. So what if you want to consider the rainfall, a transient condition, and how it is going to affect the stability of the slope? This is one more thing. And what if you have a cyclic moment during the earthquake? So what happens is during the earthquake, since it's in a sloping ground, there will be accumulated displacement because of the cyclic movement of the ground. So whether it is possible to consider in LEM, it's not, because you would not find displacement in any LEM approach. It's just providing you the factor of safety and the probable failure surface. So earthquake triggered lateral spreading and liquefaction needed to be considered as well, right? So if you're dealing with lateral spreading, and if you're dealing with the liquefaction, it is a governing thing here in New Zealand, right? So we need to consider FEM only for this approach, because in LEM, there are many assumptions that need to be considered by changing the material properties via various empirical equations to be able to understand the effects of lateral spreading and liquefaction in the slope, right? So again, FEM will be a better approach. We will see what we have in our pockets for considering all these in GTSNX, which is our geotechnical product. And how about multiple shear failures or progressive sequential slope surfaces? So what happens in reality is whenever, let's say, you're dealing with a volcanic ash and there is a lot of rainfall, and the phreatic surface has been increased dramatically, and you end up having fully saturated condition. So the failure surface may not no longer be a circular failure surface. There will be sequentially failing happening. That means one failure surface followed by some other failure surface and so on. There will be a progressive nature of development in the failure surface, which can never be considered in LEM, of course. So what FEM can be, where FEM can be useful for sure. So let's check some of it. And also, what if joint plane and the tension cracks in the rocks are to be simulated? Yes, again, FEM could be helpful in this regard. So let's check the same for slope instability or slope stability assessment in volcanic ash soils. So this has been taken from one of the recent project from one of our clients. So I would like to thank him for providing the data. So let's talk about this particular slope. So we have an Anger ash and Hamilton ash, upper Matua and so on, lower Matua, and we have a weak layer in between. So this is the soil strata as well as geology that has been considered in this study. So if I go with the just self-weight of the soil and find whether the slope is stable or not, I'm ending up finding LEM to be not stable. So you are finding the factor of safety less than 1. So it is instable. But of course, when I go with the FEM approach, so I am ending up having a factor of safety of 1.23. This is just under self-weight, no rainfall, just the initial water level condition. And you can see the initial water condition, which is well below the sloping ground. So here, there might be a lot of reasons for the increase in the factor of safety. So the reason could be a consideration of the plastic nature or of the soil. So consideration of the iterative scheme of the nonlinear solver in the FEM. So there can be many reasons, but the idea is, yeah, the factor of safety is not same as the factor of safety that we find from the LEM approach. So we have the factor of safety of 1.23 here for the complex soil strata that we have now. And how about the rainfall? So the interesting thing happens here. So if you see, because of the rainfall, the initial water level, which was well below the ground, is now almost reaching the ground over there. So that the picture on the left top, you can see that raised water level due to the rainfall. And the rainfall was applied on that surface as a boundary condition. That's the transient condition was considered in this case. So due to that, when I run the slope stability assessment, I could able to see there are multiple failure surfaces getting generated. So you can see the failure surface at the toe or this face failure on the top, and there is a circular failure surface generating in between in the middle, and there is a bigger failure surface which is passing through the thin layer over there. So all these things can only be considered in FEM because you would able to find the progressive or sequential failure surfaces which are developed due to rainfall, and the factor of safety over here is like 1.05. So under self-weight it was 1.23, and under rainfall it now is 1.05. So it has been reduced. So which is an important fact for volcanic ash soil, because in the volcanic ash soils, when it becomes saturated, it becomes it starts failing. And this is how the pore pressure distribution that you would find in FEM. So because of the seepage assessment and how that seepage assessment is going to affect the stress condition and so on. So the increased phreatic surface on the left top, and the right bottom is the pore pressure distribution. So you can see the pore pressure distribution is varying significantly throughout the slope because of the topography and rainfall and infiltration properties, permeability, hydraulic conditions, basically. And coming to the next important part, the tension cracks. So this is one of the very random profile that I had. I was able to get it out from the internet. So this is for one of the like a Kaikor earthquake condition, and this is the slope for that. And here I was able to model the entire joint plane, and there was a sedimentary rock and there was a gravic rock. And because of the modeling of the joint plane, I was able to find the failure surface mostly situated only in the sedimentary rock. And even that, as you can see, multiple failure surfaces developed over there because of the tension cracks that are being generated. So it is like one part of the sedimentary rock being failing, and followed by the other part, and so on. So the right bottom like GIF file can help you out in better understanding of the tension cracks that could have been developed because of the joint plane in the sedimentary rock. So this is one such example, and this can only be developed in, again, FEM. So coming to the earthquake, so seismicity is a very important part in New Zealand. And most of the times we end up dealing with pseudostatic method for the slope stability assessment here. And here we go. So because of the pseudostatic assessment of this very simple slope that I had carried out, in LEM we found like 1.5, but again, in FEM, considering the strength reduction method for a pseudostatic method, I found the factor of safety to be 1.5. But instead of considering the pseudostatic method, how about considering the time history assessment? That means you're considering the entire ground shaking. So again, New Zealand guidelines is asking you to go with shaking whenever it is needed. So ground shaking analysis need to be considered again up to the users or the geotechnical engineer interpretation and discretion. So for the ground shaking, for the same model, I was able to find the factor of safety of 1.02. This could be due to the amplification of the signal that is traveling from the bottom layer to the top layer, or this could be due to the all the accumulated displacement that you could find. So here we go. So there was an amplification. You can see the red color dot is the amplification, amplified signal, the red on the left top picture. So basically in this particular case, I was able to assign the Kaiko earthquake, and I was able to, it was generally, the Kaiko earthquake was so severe, it was for 120 seconds. The ground shaking happened for 120 seconds. So I was able to assign only for 40 seconds for quick assessment in this simple analysis. So I was able to find the amplification in the ground, and the right bottom is the accumulated displacement versus time. Since the slope is not confined on the other side, we were able to find the accumulated displacement that was happening because of the ground shaking. And yes, the result is the factor of safety reduced from pseudostatic assessment of 1.5 to the ground shaking assessment of 1.02. So this is, again, one particular study wherein time history has its own implication, and it is necessary at least to consider for the important structures. So that's in general about the challenges and what kind of failure mechanisms that we could find from the slope stability and how FEM can be helpful in that regard. Now I would like to talk about the solutions that we have in our pockets, which is GTSNX. It could be helpful for both the large and small slope stability assessment. So let's see what we got. So initially, as I said, LEM is an important part. And this package, GTSNX, can help you out in finding LEM analysis, FEM analysis, both 2D and 3D under one platform. So which is very much important because even though if we want to go with FEM, it is always needed to start with LEM, right? So LEM is like an initial step. You understand the behavior, you understand what is the failure surface and the corresponding factor of safety and where it is exactly happening. And it is better to assess it with FEM depending on the nature and the requirements of your project. And thereby you will end up doing either 2D FEM or 3D FEM. And you can do everything under one platform. That's the important point. No need to get into different licenses, just one platform, all the approaches. And the other thing is, in the case of soil, construction sequence is very important. It is a case with every other project, but it's much better, much important in the soil situations, because soil is a highly nonlinear material, right? So because it is being a highly nonlinear material, as a stress changes, that means as a construction sequence changes, its behavior changes, right? As the stress changes, the behavior changes, and thereby the nature of the soil could change from elastic to plasticity at any given point of the time, depending on loading or unloading situations that is happening in the site. So here in this software, of course, you can consider all the construction sequencing, and you will be able to find the factor of safeties and the failure surface for each and every stage for a particular local assessment or a global assessment. Yeah, this software offers you the SRM for construction sequencing as well, or the slope stability assessment for construction stages. And the next thing is, now, yeah, we are able to find that the slope is unstable. So what do we go with stabilization? There are various ways, like you can deal with soil nails, rock bolts, piles, or maybe geogrid. So geogrid, again, has been becoming a more abundant for slope stability assessment. So yes, we can do provide geogrid in this software. The important thing is geogrid being only tension-only element has to be implemented in such a way like being, it should be able to only take tension, no compression at all. So instead of modeling the geogrid as elastic material, it should be modeled as a tension-only material, wherein it can only take in tension, and thereby you can see how the factor safeties are changing because of it taking only tension, and you will end up finding what is the axial force coming in the geogrid. So if that axial force, basically the tensile force, is greater than your manufacturer criteria or not, we can end up having an idea, and then we could see, okay, geogrid is not failing or failing. Yes, so we have an geogrid which is a non-isotropic material and tension-only material present in this software for stabilization of the slope, or even MSC walls as well. And another approach I was talking initially, right? So the another approach in FEM is the strength analysis method. It's a kind of hybrid method. So it was developed in the late 1900s. And yeah, what happens over here is you're still dealing with the slip circle surface, But instead of considering the Bishop method, Felonius, Yambu, Mogishan Price, and so on, it considers the FEM approach for calculation of driving and resisting forces. So it's one of the interesting approach and has been getting popular nowadays. And yes, we do have this approach in this software for so long. So you can still consider slip circle surface. You can provide the area of interest that you wanted to analyze, and you can still find the consideration of the plasticity nature of the soil because you're dealing with FEM analysis. And the important part in New Zealand, again, we need to consider the seepage effects, basically, which could be like back related to your rainfall. So it is needed to consider rainfall and thereby how the rainfall is going to affect the stability of your slope and thereby how your slope factor of safety is changing. So here is one example. So without seepage, you're finding around the factor of safety of 2.45, but with seepage effect, you can see the factor of safety of 2.1. This is the earthen dam situation. On the upstream side, you have the water level. So because of the water level, there was hydrostatic force working on the dam. And because of the seepage movement from upstream to downstream, you can only find the failure surface getting developed only on the downstream, not on the upstream side. So if you're doing a rapid drawdown condition, there is a possibility of finding the failure surface on the upstream side as well. So both can be assessed in the same software, but it has to be integrated with flow and a mechanical behavior. So we have an opportunity to consider flow and mechanical coupled analysis using this software. And MSC walls. So MSC walls where the geogrid and the fascia plates need to be modeled. Yes, you can actually consider all the geogrids as well as fascia walls and the construction sequencing, and you will end up having the factor of safety assessment can also be done. So yes, we can deal with MSC walls as well. And dynamic slope stability, which is, again, a very important part here. And I already covered a small study on dynamic slope stability when you want to consider both pseudostatic as well as dynamic slope stability with SRM. So here, we have an interesting analysis called time history assessment plus SRM. So you can let the software analyze for ground shaking. Maybe you will end up having a 20-second earthquake to be inputted to the software. And maybe in that 20-second, you can ask the software to analyze the slope stability at 15th second or maybe 20th second as well. So you can let the software know at what point of the time during the earthquake the stability of the slope is. So this is one interesting thing wherein it could be applicable for any kind of slope. And even not just seismic load, but you can apply for other kinds of dynamic loads like the terrain dynamic load here. So the terrain dynamic load, the terrain is moving and how the embankment failure is happening. So not just seismicity, but other dynamic loads can also be considered. And liquefaction, again, the important part. So in the case of liquefaction, the pore pressure development and at the same time how the shear stress reduction is happening, that is important. And we can consider that using various constitutive models in this software. So we have UBC SAN as well as PM4 SAN, which can help you out in accumulation of the pore pressure ratio that you're finding here, and how the layer is going to have no strength at the end of the day because of the liquefaction, and how the pile's behavior will be changing with respect to time can easily be assessed here. So this will be very much helpful for detailed assessment of maybe a simple building or maybe a bridge or maybe for a slope stability assessment. So could be of any condition. So you can assign all these materials and maybe ask the software to assess the slope stability at any point of the time. And consolidation plus SRM, since soft soil is also predominant in New Zealand, so maybe consolidation, long-term settlement might be very important in many parts, maybe for motorways or embankments and different situations. So we can model the consolidation, and we can also go with the ground improvement and see before and after effects of consolidation on our ground improvement techniques on the embankment. So you can see what is the failure surface and the factor of safety before and after ground improvement on the embankment. So even this kind of situation is possible in this software. So to do all these things, we need to have a proper modeling tools, right? So you wanted to create a simple slope. Yeah, you can directly create and using the AutoCAD related functions in this software. Otherwise, let's say you wanted to create a 3D slope. So we have many features for creating the terrain model for the large slopes. So suppose you're dealing with a hilly terrain, you can take into the contour data or maybe LiDAR survey data, so the elevation data, that can always be converted to a surface, which is a terrain. And later on, you can always import the borehole data to get the soil profile or strata developed in this software easily. So previously, again, modeling is the important part, but takes a lot of time initially. But due to the advancements in the modern tools, the modeling has been made easy. And at the same time, the computation has been increased. So yes, it will take a greater time when you compare with other LEM tools, but yeah, very less time when you compare with the previous generation of FEM tools. And of course, instead of just contour data, you can take into the LiDAR survey or elevation data and convert that to a surface, and that can be obviously taken back to a 3D model. And instead of modeling, you can always import all these files. So every other consultant might be using different softwares. Some might be using Leapfrog, some might be using Civil 3D, some might be using other softwares. You can import all those models here. Thereby, you will be able to create the assessment for slope stability or any other profile. So we have all these options available to import various model files. And if you are dealing with a block model, even block model can be inputted as a direct mesh. You can completely ignore the modeling definitions of geometry. Simply import the block model, which will help you out for the creation of the direct mesh in this software. So even this kind of interoperability is present. And of course, this can be helpful for landslide. So once the 3D model is developed, you will be able to create this kind of landslide assessment. So instead of simplifying this slope to a 2D model or a 2D profile, it's always better to consider a 3D profile in these big, large slopes because of confining stresses is very different in 3D model or when you compare with a 2D model. And lastly, now you went with a 3D model, but when you consider FEM, you will end up having a failure surface in a global area. Maybe that area it will be of no interest for you, but you can still consider the local slope assessment. You can just select the area of interest, and you'll be able to find the factor of safety in that particular area. So in area 1, you wanted to find the factor of safety. In area 2, you would be able to find the factor of safety. So all these things can be done in a single model. Both local as well as global slope assessment can be done. So yes, that's the idea from today's presentation. So yeah, happy modeling. If you have any questions, I'm happy to answer.
Thank you so much for that insight. Fascinating for those of us who've lived through the Kaikoura earthquake. Really interesting to see how far things have come across. I'm going to ask all the presenters to go up the front because we've got quite a number of questions from online. Probably easier if you're all just standing up there together and you can take those. Is that okay? Just go stand in the center. And while we're doing that, are you going to put the QR code up? All right. So just a plug for those of you in the room and online. This is the QR code with the incentive that you will get, that you can win a prize off it. So please fill this in. It's about a 2-minute survey. But I believe, Danny, you're going to ask the questions.
Sure am. The first question is for Willem. What is the biggest challenge you encountered as a design engineer with using the various combinations of software?
It's a good question. I think the biggest challenge I find is you stitch together something that you think works great, and then you test it and it works, and then someone else tries it and there's something just ever so slightly different. And if it's a different person using a tool that they didn't develop, the difficulty is finding a way for that person. So like I said in my presentation, whatever you do needs to be adaptable so that person can still make it suitable for what they're trying to do. I think that's probably the biggest challenge.
Thank you. Another question for you, Willem. Have you, in your experience, found it trying to collaborate these innovations between structural and geotech engineers so both sides can engage with API?
I think currently we haven't tried these tools from a geotech and a structures perspective together. Like, yeah, MIDAS has got the capability to do this geotech analysis as well. And it's definitely something I'm interested in, but haven't tried just yet.
Thank you. The next question is for Pranev. Have MIDAS Gen for building and MIDAS Civil already integrated New Zealand code, seismic, winds, steel, concrete, timber, etc.?
Okay. So it has, I would say, almost all the codal standards, materials, sections. I think we have been through those in the presentations part. For the concrete part and for the, loadings and for design, I think we are just a month behind. Within next month, it would be released with the newest update in the software. Thank you.
Awesome, thank you. Another question for you. Can MIDAS be used in a similar way to perform 3D for the non-linear analysis and design of high-rise buildings?
Oh, perform a 3D?
Yeah.
Yes, okay. All right, yes, definitely. I mean, especially in, it has been already been used widely in regions such as Philippines, which I believe as much as seismically active as New Zealand. So there are a lot of even stadiums, Olympic stadiums, buildings which are used for retrofitting as well as new buildings over there. So yes, it can be utilized. Thank you.
Thank you. Final question for you. Can MIDAS be used to design for seismic strengthening for existing buildings?
Yeah, absolutely. So similar to buildings, yes, for bridges as well, it can be used for strengthening the seismically active regions.
Awesome, thank you so much. The next question is for Pankaj. This is for the asset management point of view. Generate a maintenance rehabilitation program for next 4 years and request funding.
Well, I think in today's era, data is the asset. That's the new currency these days. So coming to the point, data management or for asset managers, particularly one of the applications which I see where softwares like MIDAS can be applied is for data preservance, for storing the existing model files, which has data of the structures which are out there in public service. So as and when required, or for future maintenance works, for rehabilitation works, or for understand if there's any emergency, if there's any accident, to quickly call back the previous model files and see if it's safe to be open for public access. For such quick reviews, MIDAS softwares like MIDAS can be applied. And coming to the forward 4-year program, which is the later part of the question, it's matter of future, I think, but with tools like API, I'm pretty sure forward program does offer integration through API as well. So there is a possibility, but we'll have to, of course, double check with the developers there on the other side.
Thank you. Where can we get the plugin for the calculation of PY curves?
So all the plugins are available out there on our technical support website. And for the few which are tailored for New Zealand specific applications, we would be able to offer them on request, on demand. So your team engineers can reach out to us definitely for that. And these are available for no additional cost, to be transparent on that.
Awesome, thank you. Would you be able to provide us with a training manual that outlines the step-by-step process in accordance with New Zealand regulations?
Yeah, we do have step-by-step tutorials available for our software in specific to New Zealand standards. We would be happy to share that upon our request received by us. And not just that, we have gone a step ahead. We have design calculation guideline, which closely aligns with the back math of the software, as well as relating it with the New Zealand local codal guidelines. So we would be happy to share that as well in regards to NZ specific requirements.
Thank you. One last question for you. When is the training and how can we sign up? Very keen on it.
Well, thank you for the interest in advance. The training session we are coming up with would be on 4th and 6th of November. It's going to be covering aspects of API integration, automation, workflow setup. So we would be sending the invite link maybe next week, and would be happy to see you all there.
Awesome. Thank you, Pankaj. The next question is for Graham. Question is, what boundary condition did you use for the fluid at the end of the reservoir?
So at the end of the reservoir, you need basically it's a non-reflecting boundary condition. So it doesn't reflect the pressure waves back onto the structure. That's the boundary condition.
Awesome. Thank you. That was the last question for you, Graham. So then we just have one for Harsha. In the PVD, prefabricated vertical drain consolidation analysis, can the consolidation process be modeled to verify the consolidation period, or do we simply input the soil parameters from the site investigation and carry out only the stability analysis?
So this is a consolidation analysis plus SRM coupled one, which I was showing you in the slide. So of course, you will be able to input all the permeability conditions and all the water level conditions that is existing in the site, and you provide the PVD. And at the end, you will be able to find how the settlement versus time is happening. Thereby, we can back calculate the degree of consolidation. And not just that, you will be able to find per pressure variation. And again, that will help us in back calculation of the entire degree of consolidation that was found over both the secondary as well as primary consolidation.
Thank you. That's all for the online questions. Any questions in the room, Tanya?
Any questions in the room? No, I think you've answered everything. Thank you once again. I'll let you go back to your seats and I will. Well, wow, that has been a very full afternoon. I have learned so much, and I imagine that all of you in the room and online will be saying the same. Lot to think about. So please, as we said at the beginning, this is a first for us in a partnership of this manner. I know others, I've talked to in breaks, other organisations do this kind of thing, but we're really keen to get your feedback, not only on what you've heard today, but your feedback on this kind of format. So please give us warts and all, either through this, but also don't hesitate to send us an email. I'm the only Tanya that works here, so if you send to our number, you will get me straight away. Remembering the freebies that I mentioned earlier. And just to be clear, MIDAS has very generously offered all attendees 6 months of the MIDAS CAD license and will provide attendees with the complete suite free for a year upon purchase of any of the MIDAS products. So please make sure you take advantage of that. And also they're happy to do project-specific, customized one-on-one training if required. So please do reach out to them, all the things that they have said. The last, a lot of thanks. So thanks to MIDAS for taking a chance on us. We really appreciate the partnership and giving it a go today. Thank you to our speakers, Pankaj, Willem, Pravna, Graham, and Harsha. The knowledge you shared was amazing. Brilliant. Thank you all so much for that. Thanks to Luke on our Engineering New Zealand staff for putting this together, and Danielle and Mackenzie who are helping us with the online stuff today and all the questions. Thank you so much. I hope this leaves you inspired, informed, and ready to make better decisions. And with that, ka kite anō, and we will say goodbye to the online audience. Thank you.